Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to get comfortable, to let the day finally settle behind you. Where in the world are you watching from? A quiet bedroom where the light has already faded? A cosy corner where you finally carved out some peace? Wherever you are, you're exactly where you need to be. Tonight we're going to explore something that shouldn't exist, but does. We're going to talk about antimatter, the rarest substance in the entire universe, a mirror reflection of everything we know that appears for the briefest instant before vanishing in a flash of pure energy. We'll discover why the universe is made of matter instead of nothing at all, understand the experiments happening right now beneath the mountains of Switzerland, and contemplate what it means that we exist in a cosmos that seems fundamentally unbalanced. It's a journey that spans from the first microsecond after the Big Bang to underground laboratories where scientists trap single atoms in magnetic bottles, from theoretical physics to the deepest questions about why anything exists at all. But don't worry, this isn't going to be a physics lecture that leaves you confused and anxious. Instead, we'll move slowly and carefully through one of the universe's most beautiful mysteries, taking our time with each discovery, each question, each wonder. By the end, I think you'll find something peaceful in the asymmetry that made our existence possible, a kind of gratitude for the cosmic accident that left us here. If you enjoy these calm explorations of the universe's quiet mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with these late hours. So settle in, let your shoulders drop. Take a slow breath and feel your body begin to release the tension you've been carrying. And let's begin our slow drift through the story of antimatter, the substance so rare that a single gram of it would be worth more than all the gold ever mined on Earth. There's nowhere you need to be right now, nothing you need to do. Just listen and let the story unfold. Let's start with something that sounds like science fiction but is absolutely real. For every particle that makes up you, this room, this planet, there exists a mirror version, identical in almost every way, but with one critical difference. An electron has a negative charge. Its antimatter twin, called a positron, has a positive charge. A proton carries a positive charge. An antiproton carries a negative one. Neutrons, which we think of as neutral, have antimatter versions too, with their internal quarks reversed. This sounds like an elegant symmetry, doesn't it? A perfect balance. A universe where for every particle there exists an equal and opposite antiparticle. And in the mathematics, in the beautiful equations that describe the fundamental nature of reality, this symmetry is absolute. Physics doesn't prefer matter over antimatter. The laws that govern one govern the other identically. They should exist in equal amounts. The universe should be perfectly balanced. But it isn't, and that simple fact is one of the most profound mysteries we've ever encountered. Look around you, at the world that surrounds you right now. The walls, the ceiling, the air you're breathing, your own body, all of it is made of matter, regular matter, electrons orbiting protons and neutrons, atoms combining into molecules, the familiar substance of existence. Antimatter is so rare in our universe that we measure it in individual particles, fleeting traces that exist for nanoseconds before annihilating. In all the vast cosmos, we've never found an antimatter star, an antimatter planet, an antimatter galaxy. Everything we can observe from the nearest asteroid to the most distant quasar is made of matter. This asymmetry shouldn't exist. According to our best understanding of physics, the Big Bang should have created matter and antimatter in precisely equal amounts. And if it had, if the universe had been perfectly balanced, something catastrophic would have happened. Something final. When matter meets antimatter, they don't bounce off each other or combine into something new. They annihilate. Completely. Both particles vanish, converting their entire mass into energy according to Einstein's famous equation. It's the most efficient energy conversion possible in the universe. Total transformation of matter into pure radiation. If the early universe had contained equal amounts of matter and antimatter, they would have found each other in the primordial chaos, annihilated completely, and left behind only light, only energy. No atoms, no stars, no planets, no you. But we're here, and this brings us to something I find deeply fascinating, the question that will guide our entire journey tonight. Somehow, in the first fractions of a second after the Big Bang, something broke the perfect symmetry. For every billion particles of antimatter created, there were 1,000,000,001 particles of matter. That tiny imbalance, one extra matter particle for every billion pairs, is the reason everything exists. After all the annihilation ended, after all the antimatter found its matter counterpart and vanished in flashes of energy, there was a small residue left over. Lonely matter particles with no antimatter partners to destroy them. That residue is everything. Every star that's ever burned, every world that's ever formed, every living thing that's ever wandered at the night sky. All of it exists because of an asymmetry so small it seems like a cosmic rounding error. 1 part in 1,000,000,000? The narrowest possible margin between existence and oblivion, and we have no idea why it happened. We know it must have happened. We're the evidence, the proof that walks and talks and asks questions. But the mechanism, the reason, the how of this asymmetry remains one of physics' greatest unsolved problems. The standard model of particle physics, our best theory for how the universe works at its smallest scales, can't explain it. Something happened in that first microsecond, something we don't yet understand, that preferred matter over antimatter by the tiniest possible amount. Which brings us gently to the question we'll spend the next few hours exploring. What is antimatter? Where did it go? Why are we here instead of nothing at all? And what are scientists doing right now in laboratories deep underground to understand this cosmic mystery? The answers, as we'll discover, are strange and beautiful and deeply humbling. Let's begin with the man who first imagined antimatter's existence, decades before anyone could prove it was real. In 1928, a quiet British physicist named Paul Dirac was working on a problem that had been troubling the scientific community. Quantum mechanics, the revolutionary new physics of the atomic realm, had been wildly successful at explaining the behaviour of electrons. But there was a problem. The equations didn't account for Einstein's theory of special relativity. They worked fine for slow-moving particles, but at speeds approaching light, they broke down. Dirac set out to fix this. He wanted an equation that would describe the electron while respecting both quantum mechanics and relativity. And in one of the most remarkable feats of pure mathematical reasoning in history, he found it. The equation was beautiful, elegant, compact. It worked perfectly. There was just one small problem. The equation had 2 solutions. One described the electron exactly as expected, a particle with negative charge and a certain mass. But the other solution described something else, a particle with the same mass as an electron but with positive charge, a mirror particle, an anti-electron. Dirac's first instinct was to dismiss this second solution as a mathematical artifact, a quirk of the algebra with no physical meaning. But the more he studied his equation, the more he realised he couldn't simply ignore this prediction. The mathematics was too compelling, too symmetrical. If the equation correctly described reality, then these anti-electrons had to exist, somewhere. This was an extraordinary claim. Dirac was predicting the existence of a form of matter that had never been observed, never been imagined, based purely on the logical implications of an equation. It was physics at its most abstract and theoretical, and many of his colleagues were sceptical. Where were these anti-electrons? Why had no one ever seen one? If they existed, why weren't they more common? Dirac couldn't answer these questions. He could only point to the mathematics and say, This is what the equation predicts. Reality, he believed, must be consistent with the deep mathematical structures that describe it. If the math says anti-electrons exist, then they exist. It took just 4 years for Dirac to be vindicated. In 1932, an American physicist named Carl Anderson was studying cosmic rays, high-energy particles from space that constantly rain down on Earth's atmosphere. He was using a device called a cloud chamber, which makes particle tracks visible by the trails of condensation they leave behind as they pass through supersaturated vapour. Anderson noticed something peculiar. Most of the tracks curved in one direction when he applied a magnetic field. These were regular electrons, behaving exactly as expected. But occasionally he saw a track that curved the opposite way. Same mass as an electron, judging by the curvature, but opposite charge. A positive electron. He had discovered the positron, Dirac's anti-electron, the first antimatter particle ever observed. The mathematics had been right. The mirror particles existed. This discovery opened an entirely new chapter in physics. If positrons existed, what about antiprotons, antineutrons? Could there be antimatter versions of every particle? The answer, as experiments over the following decades would prove, was yes. Every particle has an antiparticle counterpart. The universe is more symmetric than we ever imagined. But this symmetry made the absence of antimatter in the observable universe even more puzzling. If particles and antiparticles are created in pairs, if they're perfect mirrors of each other, if the laws of physics treat them identically, why is our universe made almost entirely of one and not the other? Dirac's equation could predict antimatter's existence, but it couldn't explain antimatter's absence. The positron that Anderson detected in his cloud chamber had been created by a cosmic ray collision high in the atmosphere, a tiny burst of energy transforming into both a particle and an antiparticle, and that positron existed for maybe a millionth of a second before encountering an ordinary electron and annihilating in a flash of gamma rays. It was a fleeting visitor, a brief manifestation of the universe's hidden symmetry, appearing just long enough to leave a track in the vapour before vanishing forever. This pattern, antimatter appearing briefly, then annihilating almost immediately, is the story of antimatter in our universe. It exists, it can be created, but it cannot persist. It's the rarest substance in the cosmos, not because it's difficult to make, but because it's impossible to keep. And this impossibility, this fundamental instability of antimatter in a matter-dominated universe, is where our story deepens into something even more profound. Imagine two dancers approaching each other on a stage. The moment they touch, both vanish in a burst of light so bright it illuminates everything around them. This is the Annihilation Dance, the fundamental interaction between matter and antimatter, the most efficient energy release possible in our universe. When an electron meets a positron, something extraordinary happens. The two particles, each carrying the same amount of mass, cease to exist as particles. Their mass doesn't disappear. The universe doesn't allow that. Mass and energy must be conserved. Instead, it transforms completely into energy, pure electromagnetic radiation. Usually 2 gamma-ray photons shooting off in opposite directions, carrying away all the energy that was locked up in the mass of the original particles. Einstein's equation, E equals mc squared, is often discussed in abstract terms, but antimatter annihilation is that equation made visible, made real. The m is the mass of the particles. The c squared is the speed of light multiplied by itself, an enormous number. The E is the energy released, and because c squared is so large, even tiny amounts of mass release tremendous energy. A single gram of antimatter meeting a gram of regular matter would release an explosion equivalent to the atomic bombs dropped on Hiroshima and Nagasaki combined. That's more energy than you could extract from burning thousands of tons of coal, from detonating tons of TNT. It's perfect conversion, total transformation, the ultimate energy density. This is why antimatter appears so often in science fiction as a fuel source or a weapon. The energy potential is real. A spacecraft powered by matter-antimatter annihilation could theoretically accelerate to a significant fraction of light speed, making interstellar travel conceivable rather than impossible. But there's a profound practical problem that science fiction often glosses over. Where do you get the antimatter? You can't mine it. There are no antimatter asteroids, no natural deposits to harvest. Every atom of antimatter must be created, and creating it requires putting in exactly the same amount of energy that you'll get back when it annihilates. Actually, it requires much more because our particle accelerators are inefficient. We put in billions of times more energy than we get back in antimatter. Creating antimatter isn't a way to make energy, it's a way to store it. And a fantastically expensive and dangerous way at that. But there's something beautiful in the annihilation process that goes beyond the energy release. It's a kind of cosmic symmetry made visible. When a particle meets its antiparticle, they don't just destroy each other chaotically. They transform in a way that perfectly conserves everything that needs to be conserved. Charge, momentum, energy, even subtle quantum properties like spin. The universe keeps its books balanced even in destruction. And the reverse process is possible too. If you have enough energy in one place, say, in the intense radiation field near a massive star, or in the collision zone inside a particle accelerator, you can create particle-antiparticle pairs out of nothing but pure energy. A photon with sufficient energy can spontaneously transform into an electron and a positron. Energy becomes matter and antimatter perfectly balanced, both particles springing into existence simultaneously. This process, called pair production, happens all the time in high-energy environments. Around black holes, in the cores of active galaxies, in the upper atmosphere when cosmic rays strike. The universe is constantly creating tiny amounts of antimatter through these natural processes. But it's also constantly destroying it, because the antimatter particles find regular matter almost immediately and annihilate. There's a kind of rhythm to it, a cosmic breathing, energy to particles, particles to energy, matter and antimatter flickering in and out of existence, brief sparks in the quantum foam. The universe doesn't mind this dance. It happens trillions of times per second, everywhere, all the time. What the universe apparently does mind is letting antimatter persist, letting it accumulate, letting it stick around long enough to form atoms and molecules and stars. And this brings us to the central question we keep circling back to, the mystery at the heart of our existence. If matter and antimatter are created together, always in perfect pairs, if the laws of physics are symmetric, why didn't everything annihilate in the beginning? What broke the symmetry? What allowed a tiny surplus of matter to survive the cosmic fire and build the universe we see? To answer that, we need to go back to the beginning, to the first second after everything began. The universe began in a state of such extreme heat and density that matter as we know it couldn't exist. In the first tiny fraction of a second after the Big Bang, the temperature was so high that even protons and neutrons couldn't form. There were only quarks and gluons, fundamental particles swimming in a plasma too hot for any structure, any stability. But the universe was expanding, and as it expanded, it cooled. Think of it like a compressed gas being released. When volume increases, temperature drops. This cooling happened incredibly fast, but each drop in temperature allowed new structures to form, new possibilities to emerge. In the first microsecond, quarks combined into protons and neutrons. But this is also when matter and antimatter should have destroyed each other. The universe was filled with particles and antiparticles in nearly equal numbers, all moving at tremendous speeds, constantly colliding. Every collision between a particle and its antiparticle resulted in annihilation. The entire cosmos was a furnace of creation and destruction, particles and antiparticles blinking in and out of existence. If the numbers had been perfectly equal, this annihilation would have been total. Every proton would have found an antiproton. Every electron would have found a positron. Everything would have been reduced to radiation, to light, to photons carrying away the energy of what might have been. The universe would have become a vast expanding sea of light, cooling gradually but empty of matter. No atoms, no chemistry, no possibility for complexity, for life, for consciousness to emerge. But the numbers weren't perfectly equal. Somehow for every billion antiparticles there were 1,000,000,001 particles of regular matter. It's such a tiny difference. If you could see the early universe, you wouldn't notice this imbalance at all. The annihilation would look complete, symmetric, total. Particles and antiparticles meeting and vanishing in perfect pairs. But after all the annihilation ended, after the last antiparticle found its particle partner and vanished in a burst of gamma rays, there was a residue, one lonely matter particle for every billion photons created by the annihilation. That residue, that tiny surplus, is everything we see when we look at the universe today. All the stars in all the galaxies, all the planets, asteroids, comets, all the gas and dust floating in interstellar space. All of it comes from that 1 part in a billion imbalance. We exist because the universe failed to be perfectly symmetric. We exist because something, somehow, preferred matter over antimatter by the smallest imaginable margin. The scientific term for this is baryogenesis, the creation of more baryons, particles like protons and neutrons, than antibaryons. And we know it happened. The evidence is everywhere in the fact that we exist to ask the question, but the mechanism remains mysterious. The Russian physicist Andrei Sakharov outlined the conditions that would be necessary for baryogenesis in 1967. There would need to be processes that violate certain symmetries. There would need to be interactions that treat matter and antimatter slightly differently. And these processes would need to happen when the universe was out of thermal equilibrium, during a phase of rapid change. These conditions can exist in theory. Some processes in particle physics do treat matter and antimatter differently. We've observed this in laboratory experiments, but the differences we've measured are far too small to account for the matter, antimatter asymmetry we observe. Something else must have happened, something we haven't detected yet. Some particle we haven't discovered, some force we don't understand, some moment of symmetry breaking in the early universe that left its signature in the fundamental structure of everything. By the time the universe was 1 second old, the drama was over. The temperature had dropped enough that pair production stopped. There wasn't enough energy to create new particle-antiparticle pairs. The annihilation finished. And what was left was our universe, made of matter, filled with photons from the annihilation, beginning the long journey towards stars and planets, and eventually, after billions of years, toward life and consciousness. 1 second. That's all it took to determine the basic composition of everything that would ever exist. 1 second of intense heat, rapid expansion, and mysterious symmetry breaking. Everything since has been aftermath, consequence, the slow unfolding of possibilities that were locked in during that first fierce moment. And the antimatter, it vanished, almost completely, leaving behind only the question of why it lost the cosmic lottery, and where we might still find traces of its brief existence. If you were an astronomer looking out at the universe, trying to determine whether distant objects were made of matter or antimatter, you'd face a surprisingly difficult challenge. A hydrogen atom looks exactly like an antihydrogen atom. It has the same spectral lines, emits the same light, behaves the same way under gravity. From a distance, an antimatter star would be indistinguishable from a regular star, but there would be one telltale sign: boundaries. If there were regions of antimatter out there, antimatter galaxies, antimatter clusters, there would have to be places where antimatter and matter met. And at those boundaries you'd see annihilation, a constant, tremendous release of gamma rays as atoms from one side encountered atoms from the other side, and destroyed each other. So astronomers have looked. They've searched for the gamma-ray signatures that would indicate matter-antimatter boundaries in space. They've looked for evidence of antimatter galaxies, antimatter clusters, antimatter regions. And they found nothing. No boundaries, no annihilation zones, no large-scale antimatter structures anywhere we can observe. The universe, as far as we can tell, is made entirely of matter. From our local group of galaxies to the most distant quasars, from nearby nebulae to galaxy clusters billions of light years away, it's all matter. The asymmetry isn't just local, it's cosmic. The entire observable universe, stretching tens of billions of light years in every direction, seems to be made of the same stuff we are. This is both reassuring and deeply puzzling. Reassuring because it means we're not at risk of accidentally encountering an antimatter asteroid or antimatter cloud. Such a collision would be spectacularly catastrophic. But puzzling because it means the matter-antimatter asymmetry wasn't a local fluctuation. It was fundamental, built into the universe from the beginning. There is one place where we do detect antimatter regularly, though in tiny amounts. Near the centre of our galaxy, there's a faint glow of gamma rays with a very specific energy. 511,000 electron volts. This is the exact energy released when an electron and positron annihilate. Something near the galactic centre is creating positrons, and they're encountering regular electrons and annihilating. We're not entirely sure what's creating these positrons. It could be radioactive decay from massive stars. It could be pulsars, rapidly rotating neutron stars that generate enormous magnetic fields. It could be cosmic ray collisions. Whatever the source, the positrons don't travel far before annihilating. They're created. They exist for perhaps seconds or minutes, and then they're gone. There's also antimatter in cosmic rays, the high-energy particles that constantly bombard Earth from space. Satellites have detected antiprotons and positrons in these cosmic rays. But again, these are likely produced by collisions, by high-energy processes that create particle-antiparticle pairs. They're not evidence of primordial antimatter surviving from the early universe. They're newly created brief visitors. Some physicists have wondered whether there could be antimatter regions beyond our observable horizon. Maybe the asymmetry that favoured matter in our region favoured antimatter elsewhere, and we just can't see that far. It's an intriguing idea, but it doesn't solve the fundamental problem. Even if there are antimatter regions beyond what we can observe, the question remains. Why did the universe separate into matter and antimatter regions instead of mixing completely and annihilating? The most likely answer is that there are no large antimatter regions. The asymmetry was uniform. Everywhere in the universe, matter outnumbered antimatter by the same tiny fraction. And everywhere, after the annihilation finished, matter was left behind. This means that antimatter, in any substantial quantity, is genuinely the rarest thing in the universe. You could travel to every star, explore every galaxy, drift through every nebula and void, and you'd find only trace amounts, fleeting particles created by high-energy processes and destroyed almost instantly. If you wanted to find antimatter, to study it, to understand its properties, you couldn't go looking for it in space. You'd have to make it yourself. You'd need particle accelerators, sophisticated detectors, magnetic traps to hold it without letting it touch any regular matter. You'd need some of the most advanced technology humanity has ever developed. And that's exactly what scientists have done. Deep underground, beneath the mountains on the French-Swiss border, there's a laboratory where they create antimatter atoms one at a time, trap them in magnetic bottles, and study them with exquisite precision. This is where our understanding of antimatter is being refined, where the mystery of the cosmic asymmetry is being probed. Let's descend into that underground world and see what they've learned. Beneath the peaceful countryside on the border between France and Switzerland, there's a tunnel. A circular tunnel 27 kilometres around, buried 100 metres underground. This is the Large Hadron Collider. the world's largest and most powerful particle accelerator. But the LHC is just one part of a vast complex of accelerators, detectors, and experimental facilities known as CERN, the European Organisation for Nuclear Research. And at CERN they make antimatter, not in the dramatic quantities of science fiction, but in carefully controlled amounts, particle by particle, using some of the most sophisticated technology ever developed. The process begins with hydrogen, the simplest and most abundant element in the universe. Regular hydrogen atoms are stripped of their electrons, leaving just protons, bare atomic nuclei. These protons are accelerated to nearly the speed of light and smashed into a metal target. The collisions release enormous amounts of energy, and some of that energy transforms into matter-antimatter pairs, according to Einstein's equation working in reverse. Most of what's created. Before we continue, I want to pause for just a moment, because what you have learned in the last 30 minutes is something genuinely rare. Most people move through their entire lives without ever stopping to understand the world at this level, but you did. Tonight you chose curiosity over noise and depth over distraction. That is exactly who this channel was made for. If you want to keep being that person, a like and subscribe takes 2 seconds and make sure this channel never stops finding you. Now, let's go deeper. Most of what's created is a chaotic spray of particles. Mesons, muons, all sorts of exotic particles that exist for microseconds before decaying. But among this debris there are antiprotons, particles identical to protons in every way except for their negative electrical charge. These antiprotons are moving at tremendous speeds, far too fast to work with, so they're fed into another accelerator called the antiproton decelerator. This device does exactly what its name suggests. It slows the antiprotons down using electric fields and focusing magnets. Over the course of several minutes, the antiprotons are cooled from nearly light speed to speed slow enough that they can be captured and trapped. Even at these slower speeds, you can't just put antiprotons in a container. They're still moving, still energetic, and most importantly, they're made of antimatter. If they touch the walls of any physical container, they'll annihilate instantly. So instead, scientists use magnetic fields to create what's called a penning trap, essentially a magnetic bottle with no physical walls. The antiprotons are held suspended in space by carefully shaped magnetic fields that push them away from the walls without actually touching them. But antiprotons alone aren't enough if you want to study antimatter atoms. You need positrons too, the antimatter equivalent of electrons. These are easier to obtain. Positrons are naturally produced by certain radioactive isotopes. Sodium-22, for example, emits positrons as it decays. So while CERN has to create antiprotons using particle collisions, they can get positrons from a radioactive source, then trap and cool them using similar magnetic techniques. Now comes the delicate part. To make an antimatter atom, antihydrogen, the simplest possibility, you need to bring antiprotons and positrons together under conditions where they'll combine rather than just bouncing off each other. This requires extraordinary precision. The antiprotons and positrons need to be at the right temperature, the right density, moving at the right speeds. When conditions are right, when a slow-moving positron passes near a slow-moving antiproton, they can be captured by each other's electromagnetic attraction. The positron begins orbiting the antiproton, exactly as an electron orbits a proton in regular hydrogen, and in that moment, you have it, an antihydrogen atom, the mirror image of the most common atom in the universe, the rarest atom in the known cosmos. The first antihydrogen atoms were created in 1995. They existed for about 40 billionths of a second before annihilating against the walls of the experimental apparatus. Creating them was a triumph, but that brief existence wasn't long enough to study them properly, to measure their properties, to compare them with regular hydrogen and see if there were any differences. The breakthrough came with better traps. Over the years, scientists developed more sophisticated magnetic bottles that could hold antihydrogen atoms for longer periods, not hours or even minutes but seconds. then minutes, then longer still. The current record is about 16 hours. Scientists created antihydrogen atoms and kept them trapped, suspended in magnetic fields, for more than half a day before deliberately releasing them. 16 hours might not sound like much, but it's an eternity compared to those first 40 billionths of a second. It's long enough to perform experiments, to shine light on the atoms and see how they respond, to measure their properties with incredible precision. And what have these experiments revealed? Something both reassuring and frustrating. Antihydrogen behaves exactly like regular hydrogen. Exactly. Its spectral lines are identical. Its response to light is identical. Its quantum properties are identical. Within the precision of our measurements, there's no difference at all. Antimatter really is a perfect mirror of matter, at least in all the ways we can currently measure. Holding antimatter is like trying to carry water in your bare hands. It wants to escape, to touch the world around it, and the moment it does, it's gone. So the traps that hold antihydrogen atoms at CERN are marvels of engineering, invisible prisons made of precisely shaped magnetic fields. The principle is surprisingly simple, even if the execution is extraordinarily complex. Antihydrogen is magnetically neutral overall. The positive charge of the antiproton and the negative charge of the positron cancel out. But like regular hydrogen, it has a magnetic moment. It's like a tiny bar magnet, and bar magnets can be pushed and pulled by magnetic fields. The trap uses this property to create a magnetic well, a region of space where the magnetic field is weaker in the centre and stronger toward the edges. Antihydrogen atoms, being magnetic, are pushed toward the weak field region in the centre. It's like rolling marbles into a bowl. They settle at the bottom, held there not by walls but by the curved magnetic landscape. But there's a problem. This only works for cold atoms. If the antihydrogen atoms are moving too fast, they have too much kinetic energy. They can climb out of the magnetic well and escape to the walls of the physical vacuum chamber, where they annihilate instantly in a tiny flash of gamma rays. So temperature matters enormously. The antihydrogen needs to be incredibly cold, a fraction of a degree above absolute zero. At these temperatures, the atoms are barely moving, just drifting gently in the magnetic landscape, held in place by forces so subtle they wouldn't hold back a fly, but perfectly adequate to confine atoms that weigh almost nothing. Getting antihydrogen this cold is a challenge in itself. You can't touch it to cool it. That would destroy it. Instead, scientists use a technique called evaporative cooling. The hottest atoms, the ones moving fastest, escape the trap first. This gradually lowers the average temperature of the remaining atoms, like blowing on hot soup to cool it. The energetic atoms carry away heat when they leave. The traps themselves are works of art in a way. Superconducting magnets arranged in precise geometries. Cooled to a few degrees above absolute zero themselves using liquid helium. These magnets create field strengths of several Tesla, thousands of times stronger than Earth's magnetic field, shaped to create the smooth, bowl-like magnetic landscape that can hold antihydrogen atoms suspended in the centre. And there's more to the trap than just magnets. Inside, there's an ultra-high vacuum, pressure so low that there are almost no regular atoms that could collide with the antihydrogen and destroy it. The vacuum is better than the vacuum of space, better than the conditions between stars. Even a single stray molecule could spell doom for a trapped antihydrogen atom. Scientists can't see the antihydrogen atoms directly. They're electrically neutral and don't respond to most detection methods while trapped. But they can infer their presence. They know how many antiprotons and positrons they started with. They can detect the flash of gamma rays when atoms annihilate. So they can count how many atoms they've successfully trapped by seeing how long those gamma ray flashes continue. When they want to study the atoms, they have options. They can shine laser light on them and see how they respond. Antihydrogen, like regular hydrogen, absorbs light at specific frequencies corresponding to the energy levels of its electron, or rather, its positron. By measuring which frequencies are absorbed, scientists can map out the internal structure of the antihydrogen atom with exquisite precision. They can also test how antimatter responds to gravity. This might seem odd. Why would antimatter behave differently under gravity than regular matter? But some theories predict subtle differences, and the only way to know for sure is to measure. So scientists have designed experiments where they release antihydrogen atoms from their magnetic trap and watch how they fall. Do they fall down, like regular matter? Or might they fall up, repelled by Earth's gravity? Spoiler, they fall down, exactly as regular hydrogen would. Antimatter, as far as we can tell, responds to gravity in exactly the same way as matter. It's not anti-gravity. Way that antimatter atoms absorb light, or way that antimatter atoms absorb light or respond to magnetic fields or fall in Earth's gravity, there might be a clue. A tiny difference, a subtle asymmetry, something that could explain why the universe chose matter over antimatter in the beginning. There's something humbling about the scale of antimatter research at CERN. All that technology, all that expertise, all those massive accelerators and sophisticated detectors, and at the end of the process, they're working with single atoms. Sometimes dozens of atoms if they're having a good day, but never more than a handful at once. To put this in perspective, if you took a breath right now, you'd inhale about 10 sextillion molecules. That's 10 followed by 22 zeros. The air around you contains more atoms than there are grains of sand on all the beaches of Earth. Matter, regular matter, is abundant beyond comprehension. But antimatter? The total amount of antihydrogen ever created, if you gathered it all together from every experiment ever performed, would weigh far less than a single grain of that sand. We're talking about thousands of atoms total, created over decades of work. And most of those atoms existed for less than a second before annihilating. This scarcity makes every measurement precious. When scientists trap a few antihydrogen atoms and shine laser light on them, they're not performing the experiment on millions of atoms to get statistical certainty. They're measuring the response of individual atoms one at a time, building up statistics gradually over many experimental runs. And yet, despite working at this atomic scale, they've made remarkable discoveries. Or rather, they've made a remarkable confirmation. Antimatter really is identical to matter in all the ways we can measure. The spectrum of antihydrogen, the specific frequencies of light it absorbs, matches the spectrum of regular hydrogen to better than 1 part in a trillion. That's like measuring the distance from Earth to the Sun and being accurate to within the width of a human hair. This precision is only possible because hydrogen is so well understood. It's the simplest atom, just 1 proton and 1 electron, and physicists have been studying it for over a century. Its properties are among the most precisely measured values in all of science. So when they measure antihydrogen, they're comparing it to a standard we know extraordinarily well. Each measurement that shows antimatter behaving identically to matter is both a success and a frustration. A success because it confirms our theoretical understanding, because it shows that the symmetry between matter and antimatter really is as perfect as the equations suggest. But a frustration because we're still looking for the asymmetry that must have existed in the early universe. The difference, however subtle, that allowed matter to outnumber antimatter. It's possible that the asymmetry has nothing to do with the properties of antimatter atoms. Maybe antihydrogen is absolutely identical to hydrogen, and the matter-antimatter imbalance came from some other source. Some process involving different particles, different forces, operating at energy scales far higher than we can achieve in laboratories. But scientists keep looking. They keep refining their measurements, improving their precision, searching for any deviation. Any hint that antimatter might be slightly different in some way we haven't yet detected. Because if they found a difference, even a tiny one, it could revolutionize our understanding of the early universe. There's also practical knowledge gained from this work. Learning to trap and manipulate antimatter has taught physicists an enormous amount about precision measurements, about controlling particles with magnetic and electric fields, about working at the limits of what's technically possible. These techniques have applications beyond antimatter research, in fields like quantum computing and medical imaging. And there's something poetic about the whole enterprise if you think about it. Here we are, made of matter, living on a matter planet, in a matter-dominated universe, laboriously creating the rarest substance in existence just to study it, just to understand why we exist at all, its curiosity at its purest, the drive to know, to understand, to answer fundamental questions about reality, even when the answers have no practical application. Because that's the thing about fundamental science. You don't do it for the applications, you do it to understand. And sometimes, often unexpectedly, understanding leads to applications you never imagined. The scientists who first split the atom weren't thinking about nuclear power plants. The physicists who developed quantum mechanics weren't envisioning the computer you might be watching this on. They were just trying to understand how reality works at its deepest levels. The scientists at CERN, creating antihydrogen one atom at a time, are continuing that tradition. They're asking, what is the universe made of? Why does it look the way it does? And in asking, in measuring, in pushing the boundaries of what we can know, they're adding to humanity's slowly growing understanding of the cosmos we inhabit. Here's a question that sounds simple, but opens onto deep mysteries. Does antimatter fall up or down? If you held an antihydrogen atom above Earth's surface and released it, would it fall toward the ground like regular matter, or would it fall upward, repelled by Earth's gravitational field? The conventional answer, the one that almost all physicists expect, is that antimatter falls down just like regular matter. Einstein's theory of general relativity treats all forms of energy and mass the same way. Gravity doesn't care about charge, doesn't distinguish between particles and antiparticles. It responds to mass energy, and antimatter has positive mass energy, so it should fall down. But here's the thing, until recently this had never been directly tested. We had good theoretical reasons to believe antimatter would fall normally, but belief isn't the same as measurement. Science requires measurement. And measuring how antimatter responds to gravity is extraordinarily difficult because antimatter is so hard to make and trap. The difficulty is partly because gravity is such a weak force. At the atomic scale, electromagnetic forces are vastly stronger than gravity. If you have a charged particle, electric fields completely dominate its motion. Gravity's effect is tiny by comparison, like trying to detect the pull of the moon on a grain of sand while it's being blown by hurricane winds. Antihydrogen, being electrically neutral, helps with this problem. It's not pushed around by electric fields. But it's still affected by magnetic fields because of its magnetic moment, and the magnetic traps that hold antihydrogen produce forces thousands or millions of times stronger than Earth's gravity. So to measure how antimatter falls, you need to turn off the trap, release the atoms, and somehow measure their trajectory before they hit the walls and annihilate. The Alpha-G experiment at CERN, designed specifically for this purpose, achieved the first direct measurement in 2023. They created antihydrogen atoms in a special vertical trap, then released them and watched what happened, and the atoms fell down. Just like regular matter, they didn't fall up, they didn't hover. They fell, accelerating downward at Earth's surface gravity, within the experimental uncertainty. This might seem anticlimactic. Of course, antimatter falls down, right? But confirming this experimentally was crucial. There are some speculative theories, extensions of general relativity, that predict antimatter might experience gravity differently. Some even suggest it might be gravitationally repelled by regular matter. These ideas are highly speculative, not part of mainstream physics. But they're not impossible. The only way to rule them out is to measure, and now we have measured. Antimatter falls at the same rate as matter. the gravitational mass of antihydrogen is positive, just like regular hydrogen. This is a relief in some ways. If antimatter fell upward, it would mean general relativity was wrong in a fundamental way, and we'd have to rebuild much of modern physics. But it's also a missed opportunity, because a difference in gravitational behaviour would have been a spectacular discovery, a key to new physics. This measurement opens new questions, though. The precision of that first result wasn't perfect. The uncertainty was fairly large. Future experiments will measure how antimatter falls with much greater precision. And if there's any tiny deviation from the expected behaviour, any hint that antimatter's gravitational mass is slightly different from its inertial mass, that could be revolutionary. There's also a deeper question lurking here. Why does antimatter have positive mass at all? When Dirac first predicted antimatter, his equation actually suggested antiparticles might have negative mass. He later reinterpreted this. They have positive mass but negative energy in a certain sense. But the question of why mass is always positive, why there's no negative mass in the universe, is still somewhat mysterious. If negative mass existed, it would behave very strangely. It would accelerate in the opposite direction when you pushed it. It would fall upward in a gravitational field. A mixture of positive and negative mass would behave in bizarre ways, violating conservation of energy in apparent ways, though actually just redistributing it strangely. Most physicists think negative mass is impossible, that it would lead to contradictions. But we don't have a deep theoretical understanding of why mass must be positive. Antimatter, with its reverse charges but positive mass, sits right at the boundary of what seems possible in physics. It's as strange as matter gets while still obeying the fundamental laws. And studying how it moves in gravitational fields is one more way we're probing the limits of those laws, searching for cracks in our understanding that might lead to deeper truths. If you wanted to buy a gram of antimatter, the amount that would fit in a thimble, if you could somehow contain it, the price would be staggering. By some estimates, a gram of antihydrogen would cost about $62 trillion. That's not a typo. Trillions. More than the GDP of most countries. To understand why antimatter is so expensive, you have to understand how it's made. Every antiproton requires accelerating protons to nearly the speed of light, smashing them into a target and sorting through the debris of the collision to find the antimatter particles. This process is spectacularly inefficient. You put in billions of times more energy than you get back in the form of antimatter mass. CERN's antiproton decelerator can produce about 100 billion antiprotons per minute when running at full capacity. That sounds like a lot until you do the math. A single gram of hydrogen contains about 600 sextillion protons. To make a gram of antihydrogen, you'd need 600 sextillion antiprotons. At the current production rate, that would take about 12 billion years. That's almost as long as the current age of the universe, and that's just the antiprotons. You'd also need 600 sextillion positrons, and while these are easier to produce, you'd still need to trap and combine them with the antiprotons, which is itself an enormously inefficient process. Most attempts at creating antihydrogen result in the particles annihilating before they can combine into atoms. Then there's the energy cost. CERN's accelerators consume enormous amounts of electricity. The Large Hadron Collider alone, when running, uses about the same amount of power as a small city. Creating antimatter is one of the most energy-intensive processes imaginable. You're literally converting pure energy into mass, and you're doing it one particle at a time with technology that wastes most of the energy put in. This is why antimatter will never be a practical power source or fuel, despite its frequent appearance in science fiction. You can't make energy by creating antimatter and annihilating it. You have to put in more energy to create it than you get back when it annihilates. Antimatter isn't a source of energy, it's a storage medium, and an incredibly impractical one at that. The only place antimatter might have a practical use is in space propulsion, and even that's questionable. A matter-antimatter rocket could theoretically achieve very high exhaust velocities, making interstellar travel more feasible. But you'd still need to create and store the antimatter, and the storage problem alone is enormous. How do you keep antimatter from touching regular matter during a years-long spaceflight? How do you prevent a single malfunction from causing a catastrophic annihilation? Some people have pointed out that antimatter already has a practical use: medical imaging, positron emission tomography or PET scans. Use positrons to create detailed images of the inside of the body. A radioactive tracer that emits positrons is injected into the patient. The positrons travel a short distance and annihilate with electrons in the surrounding tissue, releasing gamma rays that can be detected by sensors around the body. This creates a three-dimensional image showing metabolic activity, but the positrons used in PET scans aren't created in particle accelerators. They come from radioactive decay of specific isotopes like fluorine-18, which are created in smaller cyclotrons at hospitals. The process is much simpler and cheaper than creating antiprotons at CERN, though still expensive by most standards. The real value of antimatter research isn't in the antimatter itself, it's in what we learn by studying it. The techniques developed to trap and manipulate single atoms have advanced the entire field of precision measurement. The quest to understand why matter outnumbers antimatter drives research into fundamental physics, into questions about the origin and evolution of the universe. And there's something magnificent about the fact that we can create and study antimatter at all. 100 years ago it was purely theoretical. 50 years ago we could create it briefly but not hold it. Now we can trap it for hours, shine lasers on it, measure its properties, test how it falls in Earth's gravity. We're working at the absolute edge of what's technically possible, pushing the boundaries of human capability. That we do this knowing the antimatter has no practical value, that it costs trillions of dollars per gram, that it exists only to answer questions, that's humanity at its best, I think. Pure curiosity, pure desire to understand. We're spending enormous resources to study the rarest substance in the universe simply because it's there, because it's mysterious, because understanding it might help us understand why we exist. In 1967, a Soviet physicist named Andrei Sakharov was thinking about the early universe and the matter-antimatter asymmetry. He wasn't an astrophysicist or a cosmologist by training. His background was in nuclear weapons, though he would later become a dissident and advocate for nuclear disarmament. But he brought a fresh perspective to the question of why we exist, and he outlined 3 conditions that would need to be true for the universe to create more matter than antimatter. These conditions, now known as the Sakharov conditions, have guided research into baryogenesis for over 50 years. And understanding them helps us grasp what must have happened in the early universe, even if we don't yet know exactly how it happened. The first condition is that there must be processes that violate what physicists call baryon number conservation. Baryons are particles like protons and neutrons, and in most processes we observe, the number of baryons minus the number of antibaryons stays constant. If you start with 2 protons, you end with 2 protons. Matter can transform, but the total baryon number doesn't change. For the universe to create an excess of matter, this rule must be breakable. There must be processes that can create more baryons than antibaryons, or destroy more antibaryons than baryons. The second condition is that these processes must violate a symmetry called CP symmetry. This is where things get subtle. CP symmetry means that if you swap all particles for antiparticles and flip everything in a mirror so left becomes right, the laws of physics should look the same. For most processes, this symmetry holds. But for baryogenesis to work, some processes must treat particles and antiparticles slightly differently, must have a preference, however small, for creating or preserving matter over antimatter. The third condition is that the universe must be out of thermal equilibrium during the time when these processes operate. This is crucial because if the universe were in perfect equilibrium, every process would be exactly balanced by its reverse process. Matter creation would be balanced by matter destruction. Any asymmetry would immediately wash out. But the expanding, cooling early universe wasn't in equilibrium. It was changing too rapidly. and in those out-of-equilibrium conditions, processes could run in one direction more than the other, creating and preserving an asymmetry. These three conditions seem abstract, but they're extraordinarily powerful. They tell us exactly what kind of physics we need to explain the universe's composition. And here's what's both encouraging and frustrating. We know that all three conditions can be met in principle. Processes that violate baryon number exist in theoretical extensions of the Standard Model. CP violation has been observed in experiments with particles called kaons and b-mesons. And the early universe was definitely out of equilibrium. But, and this is the frustrating part, the amount of CP violation we've observed in experiments is far too small to account for the matter-antimatter asymmetry. It's like finding the mechanism that could explain everything, then discovering the dial isn't turned up high enough. Something else must be contributing. Some particle we haven't discovered yet, some force we don't understand, operating at energies higher than our particle accelerators can reach. One possibility involves the Higgs field, the field that gives particles their mass. During the early universe, the Higgs field went through a phase transition, shifting from one state to another as the universe cooled. If this transition happened in the right way, if it created regions where the Higgs field was temporarily in an unstable state, that could create exactly the kind of out-of-equilibrium conditions Sakharov described, and if there are additional Higgs-like fields beyond the one we've discovered, they could provide the necessary CP violation. Another possibility involves particles called leptoquarks that could transform between quarks and leptons, allowing baryon number to change. These particles are purely theoretical at this point. We've never detected one, but they appear in various extensions of the Standard Model, and they could provide the mechanism for baryogenesis. There's also a fascinating idea involving neutrinos. These ghostly particles barely interact with anything, and they come in three types. If neutrinos are their own antiparticles, and there's some evidence suggesting they might be, then certain processes involving neutrinos could violate baryon number and create the matter-antimatter asymmetry. This would require neutrinos to have mass, which we now know they do, and it would require them to be quite massive in the early universe, heavier than they are now. All of these ideas are speculative, extensions beyond our proven physics, but they're not wild speculation. They're serious theoretical proposals that make testable predictions, and gradually through experiments and observations we're testing them, narrowing down the possibilities, searching for the mechanism that broke the cosmic symmetry and made our existence possible. CP symmetry sounds arcane, but it's actually a beautifully simple idea. Take any physical process, swap every particle for its antiparticle, and flip everything in a mirror. If the new process behaves exactly the same way, then CP symmetry is preserved. For decades, physicists assumed this symmetry was perfect, that the laws of nature made no distinction between matter and antimatter, between left and right. Then, in 1964, a team of physicists studying particles called kaons discovered something shocking. Kaons are unstable particles that decay into other particles. They come in two types that should be mirror images of each other, and according to CP symmetry, these two types should decay in exactly the same ways, at exactly the same rates. But they don't. One type decays slightly more often into certain final states than the other type does into the mirror image final states. The difference is tiny, less than 1%, but it's real, measurable, undeniable. CP symmetry is violated. The universe does make a distinction between matter and antimatter, at least in some processes. This discovery was so unexpected that it won the Nobel Prize. It opened up an entirely new avenue of research. If CP symmetry could be violated in kaon decays, where else might it be violated? And could this violation explain the matter-antimatter asymmetry? Over the following decades, physicists found more examples of CP violation. It shows up in the decay of b-mesons, particles containing bottom quarks. It appears in certain processes involving top quarks. each discovery has refined our understanding of how and why CP symmetry breaks down. The standard model of particle physics actually includes CP violation. It's built into the mathematics of how quarks interact through the weak nuclear force. There's a quantity called the CKM matrix, named after the physicists Kabibo, Kobayashi and Maskawa, who developed the theory, and this matrix contains a complex phase that leads to CP violation. Kobayashi and Maskawa won the Nobel Prize for showing that CP violation requires at least 3 generations of quarks, which is exactly what we observe in nature. But here's the problem. The amount of CP violation predicted by the standard model and confirmed by experiments is nowhere near enough to explain why the universe is made of matter. If the CKM phase were the only source of CP violation, the matter-antimatter asymmetry would be about 1 billion times smaller than what we observe. It's the right kind of effect, but the magnitude is wrong. This means there must be additional sources of CP violation beyond what's in the standard model. Some new physics, some particles or forces we haven't discovered yet, contributing to the asymmetry. And finding this new physics is one of the major goals of particle physics research today. One place scientists are looking is in neutrinos. These particles also come in 3 types, and they oscillate between types as they travel through space. The mathematics of neutrino oscillations includes a CP violating phase, similar to the one in the quark sector. But neutrinos are different from quarks in important ways, and their CP violation might be larger. Experiments are currently measuring this neutrino CP phase. Massive detectors deep underground watch for neutrinos created in particle accelerators hundreds of kilometers away. By comparing how often neutrinos and antineutrinos transform from one type to another, scientists can measure the CP violation in the neutrino sector, and preliminary results suggest the violation might be large, possibly even maximal. If neutrino CP violation is large, it strengthens the case for neutrino-based explanations of the matter-antimatter asymmetry. It suggests that processes involving neutrinos in the early universe might have been responsible for creating the excess of matter, but we're not certain yet. The measurements are difficult, the uncertainties are still large, and there are other explanations that don't require neutrinos at all. There's something profound about discovering that the universe has a preference, even a tiny one, for matter over antimatter. It means the laws of physics are not perfectly symmetric. They have a direction, a bias, a subtle-handedness. And this asymmetry, this tiny crack in the perfect mirror between matter and antimatter, is ultimately what allows us to exist. Because if CP symmetry were perfect, if matter and antimatter were treated absolutely identically by all processes, then Sakharov's second condition wouldn't be met. Even if baryon number could be violated, even if the early universe were out of equilibrium, any excess of matter would be exactly balanced by an equal excess of antimatter. The asymmetry wouldn't stick. It would wash out, and the universe would end up perfectly balanced, which means completely annihilated, nothing left but radiation. The fact that CP symmetry is violated, even slightly, gives the universe a way to break the tie between matter and antimatter to tip the balance. To choose sides, and it chose ours. There's a period in the universe's history that sounds like fantasy, but is increasingly supported by evidence. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion so rapid that it dwarfs anything we can observe today. Space itself expanded faster than the speed of light, doubling in size every fraction of a trillionth of a second. This is called cosmic inflation, and it might be the key to understanding not just the matter-antimatter asymmetry, but the entire structure of the universe. Before inflation was proposed in the early 1980s, cosmologists faced several puzzles. Why is the universe so uniform? Why does it look nearly the same in every direction? Why is space so flat, so geometrically simple? The standard Big Bang model didn't have good answers to these questions, but inflation solved them all at once. If the universe underwent a brief period of exponential expansion, tiny quantum fluctuations would be stretched to cosmic scales. This would smooth out any initial irregularities, making the universe uniform. It would flatten space, like inflating a balloon makes its surface appear flatter to an ant walking on it. And it would explain why distant regions of the universe that seem like they should never have been in contact look so similar. They were in contact before inflation stretched them apart. But inflation also provides something else, the perfect out-of-equilibrium conditions that Sakharov's third condition requires. During inflation, the universe was expanding so rapidly that particles couldn't maintain thermal equilibrium. Processes couldn't run in both directions equally, and when inflation ended, the energy that drove the expansion had to go somewhere. This is called reheating. The inflaton field, the hypothetical field that drove inflation, decayed into particles, filling the universe with matter and radiation. And this decay happened far from equilibrium, in exactly the kind of conditions where baryogenesis could occur. Some models suggest that the inflaton field itself could be responsible for creating the matter-antimatter asymmetry. As it decayed, if it preferentially created particles over antiparticles, or if the subsequent interactions of those particles violated baryon number and CP symmetry, an asymmetry could be generated and preserved. Other models place baryogenesis slightly later, after reheating, during what's called the electroweak phase transition. This is when the Higgs field shifted from having zero value everywhere to having a non-zero value, giving particles their mass. This transition happened when the universe was about a billionth of a second old, still incredibly early, but long after inflation ended. If the electroweak phase transition was first order, meaning it happened through bubble formation, with bubbles of the new phase nucleating and expanding through the old phase, it could create exactly the kind of departures from equilibrium needed for baryogenesis. Inside the bubbles and at their walls, conditions would be different from the surrounding space, and processes could run preferentially in one direction. This scenario, called electroweak baryogenesis, is elegant because it relies on physics we partly understand, the Higgs field, the electroweak force, rather than on completely new, unknown physics. But there's a problem. For electroweak baryogenesis to work, the Higgs boson needs to be lighter than about 70 gigaelectronvolts, and the Higgs boson we actually discovered at CERN has a mass of about 125 gigaelectronvolts, so either there are additional Higgs-like particles we haven't found yet, or baryogenesis happened through some other mechanism. There's also a fascinating connection between inflation and the nature of time itself. During inflation, the usual rules about causality get strange. Quantum fluctuations in the inflaton field become classical differences in the density of space. Microscopic randomness becomes macroscopic structure. The seeds of galaxies, clusters, superclusters, all of it traces back to quantum uncertainties during inflation, frozen into the fabric of space as it expanded. And if quantum mechanics played a role in creating cosmic structure, might it also have played a role in creating the matter-antimatter asymmetry? Could quantum fluctuations have biased the creation of particles over antiparticles not uniformly, but in a way that averaged out to a net excess of matter across the observable universe? These are deep questions, touching on the intersection of quantum mechanics, general relativity, thermodynamics, and particle physics, and we don't have definitive answers yet, but the framework is there. We know inflation probably happened. The evidence from cosmic microwave background observations is compelling. We know the universe underwent phase transitions as it cooled. We know baryon number and CP symmetry can be violated. All the pieces for baryogenesis exist. We just haven't yet assembled them into a complete verified picture of exactly how it happened. But we're getting closer, measurement by measurement, observation by observation, theoretical breakthrough by theoretical breakthrough. Neutrinos are strange particles. They barely interact with anything, passing through matter as if it weren't there. Every second, trillions of neutrinos from the sun pass through your body without you feeling anything, without leaving any trace. They're so ghostly that detecting even a single neutrino requires massive detectors deep underground, waiting for the 1 in a billion chance that a neutrino will collide with an atom. But these ghost particles might hold the answer to why we exist. There's a theory, called leptogenesis, that suggests the matter-antimatter asymmetry wasn't created directly by quarks and baryons at all. Instead, it was created first in the lepton sector, particles like electrons and neutrinos, and then transferred to baryons through processes that violate both baryon and lepton number. The key to this idea is that neutrinos might be Majorana particles. This is a technical term, but the concept is profound. Most particles are distinct from their antiparticles. An electron and a positron are different particles, but Majorana particles are their own antiparticles. A Majorana neutrino is indistinguishable from a Majorana antineutrino. If neutrinos are Majorana particles, it has radical implications. It means lepton number isn't conserved. You can have processes where the number of leptons changes, and lepton number violation can be connected to baryon number violation through certain processes in the Standard Model, meaning an asymmetry in leptons could produce an asymmetry in baryons. The leptogenesis scenario works like this. In the very early universe, when temperatures were extremely high, there existed heavy neutrinos, particles we haven't detected yet, much more massive than the light neutrinos we know about. These heavy neutrinos were their own antiparticles, Majorana neutrinos, and they decayed into lighter particles. But here's the crucial part. Because of CP violation, these heavy neutrinos decayed slightly more often into matter leptons than into antimatter leptons. The difference was tiny, but in the out-of-equilibrium conditions of the early universe, this tiny preference accumulated. An excess of leptons was created. Then, through processes called sphalerons, exotic interactions allowed by the weak force, some of this lepton asymmetry was converted into a baryon asymmetry. The math is complicated, but the result is simple. An excess of matter leptons became an excess of matter baryons. The matter-antimatter asymmetry we observe could be explained by the decay of particles we've never directly detected, operating at energies we can't reach in laboratories. This is speculative, but it's not wild speculation. It makes testable predictions. If neutrinos are Majorana particles, we should be able to observe certain rare processes, like neutrino-less double beta decay, where a nucleus emits 2 electrons without any neutrinos. Experiments are searching for this process right now, using detectors containing hundreds of kilograms of specific isotopes, waiting for the incredibly rare event. Another prediction involves the masses of neutrinos. We know neutrinos have mass. Experiments measuring neutrino oscillations proved this. But we don't know how massive they are or why their masses are so much smaller than other particles. Leptogenesis suggests a mechanism called the seesaw mechanism, where the light neutrino masses we observe are inversely related to the masses of heavy neutrinos. The heavier the right-handed neutrinos, the lighter the left-handed ones we detect. If this is right, the heavy neutrinos that cause baryogenesis had masses around 10 trillion times the mass of a proton. That's far beyond what we can create in particle accelerators, which is why we haven't detected them. But their existence would explain both the light neutrino masses and the matter-antimatter asymmetry in one elegant framework. There's something beautiful about the idea that the faintest, most elusive particles in the universe might be responsible for the most important asymmetry in cosmic history. Neutrinos, which interact so weakly that they can pass through light years of lead without noticing, which were dismissed for decades as insignificant, might be the key to our existence. And it's not just theoretical beauty. The leptogenesis scenario addresses all 3 of Sakharov's conditions naturally. Lepton number violation exists if neutrinos are Majorana particles. CP violation in the neutrino sector can be large, and the decay of heavy neutrinos in the expanding early universe automatically provides out-of-equilibrium conditions. We don't know yet if this is how it actually happened. The evidence is circumstantial. The heavy neutrinos are undetected. The CP violation in the neutrino sector is still being measured. But the framework is compelling, and every new measurement of neutrino properties either strengthens or weakens the case. Gradually we're assembling the clues, piecing together what happened in the first microsecond after everything began, using the faintest traces of those ancient processes that we can still detect today. All this theoretical work, all these elegant equations and speculative mechanisms would be meaningless if we couldn't connect them to observations. So what evidence do we have that the matter-antimatter asymmetry happened the way we think it did? What can we actually observe that tells us about the first microsecond of cosmic history? The most direct evidence is simply that we exist, that stars exist, that galaxies exist. The universe is not a sea of pure radiation, which is what it would be if matter and antimatter had annihilated completely. So we know the asymmetry exists. We can even measure its magnitude. The ratio of baryons to photons in the universe today is about 1 to 1.8 billion. For every baryon, every proton and neutron, there are nearly 2 billion photons, mostly in the cosmic microwave background. This ratio tells us how many matter-antimatter pairs must have annihilated. For every 2 billion pairs that destroyed each other, creating 2 billion photons, one matter particle was left over. This number comes from multiple independent measurements. We can count baryons by looking at the density of matter in the universe. We can count photons by measuring the cosmic microwave background. And the ratio comes out the same. It's one of the most precisely known numbers in cosmology. We can also look at the abundances of light elements, hydrogen, helium, lithium, created in the first few minutes after the Big Bang, during what's called Big Bang nucleosynthesis. The amounts of these elements depend sensitively on the baryon to photon ratio, and when we measure the abundances we observe and work backward, we get the same ratio. 1 baryon for every 1.8 billion photons. The consistency of these measurements is remarkable. There's also evidence from the cosmic microwave background itself. This is the afterglow of the Big Bang, radiation that has been travelling through space for nearly 14 billion years, reaching us from when the universe was just 380,000 years old. The precise pattern of hot and cold spots in this radiation carries information about the early universe, including the density of matter. Satellites like WMAP and Planck have measured this pattern with extraordinary precision. And embedded in those measurements is confirmation of the baryon density, the matter-antimatter asymmetry, the whole framework we've been discussing. The data fits the theoretical predictions beautifully. The universe we observe is exactly what you'd expect if baryogenesis happened the way Sakharov's conditions suggest. But we're also looking for more direct evidence of the mechanisms. Experiments searching for CP violation in neutrino oscillations are measuring whether nature treats neutrinos and antineutrinos differently. Early results from experiments in Japan and the United States suggest the CP violating phase in the neutrino sector might be large, possibly maximal, which would support leptogenesis models. Experiments searching for neutrinoless double beta decay, which would prove neutrinos are Majorana particles, are getting more sensitive every year. They haven't found it yet, but the constraints are tightening. Each non-detection tells us something about the possible masses and properties of neutrinos. Particle accelerators continue searching for new particles that could be involved in baryogenesis. Supersymmetric particles, leptoquarks, additional Higgs bosons, any of these could provide the necessary ingredients for creating the matter-antimatter asymmetry. The fact that we haven't found them yet tells us something about the energy scales involved, about where to look next. And there's an intriguing possibility on the horizon. Gravitational wave detectors might eventually be able to see evidence of phase transitions in the early universe. If the electroweak phase transition was first order, forming bubbles that collided and merged, it would have created gravitational waves with a specific frequency spectrum. Future space-based detectors might be sensitive enough to see these waves. providing a direct window into the era when baryogenesis might have occurred. All of this evidence, from the simple fact of our existence to the precise measurements of primordial element abundances to the ongoing searches for new particles and processes, paints a consistent picture. The matter-antimatter asymmetry is real. It happened very early in cosmic history. It involved violations of baryon number and CP symmetry during a period when the universe was far from equilibrium. We don't know all the details yet. We don't know exactly which particles were involved, exactly which processes created the asymmetry. But we know enough to ask precise questions, to design experiments that can distinguish between competing theories, to gradually narrow down the possibilities. And there's something deeply satisfying about this, about how observations of today's universe, measurements of particles and radiation, can tell us about the first moment of creation, how we can read the history of the cosmos in the light from distant galaxies, in the properties of neutrinos, in the ratio of baryons to photons. The universe keeps its own records, and we're learning to read them. Here's a question that might seem backward, but it opens onto something profound. Why does antimatter exist at all? If the universe is made almost entirely of matter, if antimatter is so rare and unstable, why does it appear in the equations of physics? Why is it even possible? The answer takes us to the deepest foundations of quantum field theory, the mathematical framework that describes how particles and forces work at the smallest scales, and it reveals something beautiful about the structure of physical law. When Paul Dirac derived his equation for the electron, incorporating both quantum mechanics and special relativity, antimatter appeared not as an option but as a necessity. The equation demanded it, and the reason has to do with something called relativistic invariance, the requirement that the laws of physics look the same to all observers, regardless of their motion. In quantum mechanics, particles are described by wave functions, mathematical objects that evolve in time. But in special relativity, time and space are intertwined. An event that's in the future for one observer might be in the past for another observer moving differently. This creates a problem. How can you have a wave function that evolves consistently in time when different observers don't even agree on what underscore quote underscore zero underscore means? Dirac's solution was elegant. Instead of thinking about single particles, you think about fields, entities that exist everywhere in space and time. These fields can be excited, creating particles, or de-excited, destroying particles. And crucially, the mathematics demands that for every particle excitation, there's also an antiparticle excitation. You can't have one without the other. They're two sides of the same quantum field. This is why antimatter appears in the Standard Model naturally, unavoidably. It's not that nature chose to include antimatter. It's that the mathematical consistency of combining quantum mechanics with relativity requires antimatter to exist. If you want a theory that respects both quantum principles and the speed of light limit, you must have antiparticles. There's an even deeper principle at work called CPT symmetry. This combines three operations: C for charge conjugation, swapping particles and antiparticles, P for parity, flipping space like a mirror, and T for time reversal, running processes backward. CPT theorem states that any quantum field theory that respects the basic principles of relativity must be invariant under the combined operation of all three transformations. This means that if you swap particles for antiparticles, flip everything in a mirror and run time backward, the laws of physics look exactly the same. CPT symmetry is thought to be absolutely exact, unlike CP symmetry, which we know is violated. And CPT symmetry requires antiparticles to exist with exactly the same mass as particles, exactly opposite charges, and exactly the same interactions under the strong and electromagnetic forces. So in deep sense, antimatter exists because the universe respects relativity and quantum mechanics. You can't have a consistent theory of particles without also having antiparticles. The mirror is built into the structure of reality. But this raises another question. If antimatter is required by the fundamental laws, if it's not optional, why is it so rare? Why did the universe end up made almost entirely of matter? And here we touch on something subtle about the difference between what's possible and what's actual. The laws of physics allow for antimatter, require it even, but they don't require it to be abundant. They describe what can happen, what's permitted, but they don't dictate the initial conditions of the universe or the specific historical path that unfolded. It's like saying the rules of chess allow both players to move pieces, but the rules don't determine which pieces end up where at the end of a particular game. The laws of physics allowed the universe to create matter and antimatter equally, and they allowed processes that could violate the balance between them. What actually happened, the specific sequence of events that led to our matter-dominated universe, is a historical fact, not a logical necessity. This distinction between laws and initial conditions is important. The laws are timeless, universal, the same everywhere. But initial conditions are contingent, specific, the particular way things happen to be at the beginning. And our existence depends on both. On laws that allow matter and antimatter to exist, and on initial conditions and early universe processes that created a slight imbalance favouring matter. There's a kind of cosmic luck in this, a contingency that might make you pause. The laws permit our existence. But the history of the universe's first 90 minutes, you've been here for 90 minutes, quietly, patiently, choosing this over everything else the world was offering you tonight. Do you know how rare that is? Most people cannot sit with something slow and meaningful for more than a few minutes before reaching for something louder. But not you. Not tonight. This channel exists for exactly this kind of person, and a like and subscribe is how we find more of them. It is how we find each other. Thank you for still being here. Now let's continue. But the history of the universe's first microsecond determined it. Change the initial conditions slightly, change the strength of CP violation, or the timing of phase transitions, and the outcome might have been different. We might not be here. Nothing might be here except cooling radiation. But the dice fell the way they did. The asymmetry emerged. And antimatter exists now, primarily as a theoretical necessity, a mathematical requirement, appearing only briefly when energy transforms into matter before vanishing again almost instantly. Some physicists and cosmologists have asked whether our universe is the only one. If there's a multiverse, many universes, each with potentially different properties, then the matter-antimatter asymmetry might not need a deep explanation. We just happen to live in the universe where matter won, because those are the only universes where observers could exist to ask the question. This is an application of what's called the anthropic principle. The idea is simple. We necessarily observe a universe compatible with our existence. If the matter-antimatter asymmetry hadn't happened, we wouldn't be here to wonder about it. So in a multiverse containing all possible outcomes, we'd inevitably find ourselves in a universe where the asymmetry worked in matter's favour. There's something unsatisfying about this explanation to many physicists. It feels like giving up on finding a mechanism, on understanding why things are the way they are. It turns a deep question about physics into a selection effect, like asking why we live on a planet instead of in empty space. We live here because this is where we can live, not because there's something special about planets in general, but the anthropic principle isn't necessarily wrong just because it's unsatisfying. If the multiverse is real, if there truly are countless other universes with different properties, then anthropic reasoning might be appropriate. The question is whether we have any evidence for such a multiverse. The eternal inflation scenario suggests we might. In this model, inflation doesn't end everywhere at once. Different regions stop inflating at different times, and each region that stops becomes its own bubble universe. These bubble universes can have different properties, different values of physical constants, different particle masses, even different numbers of spatial dimensions. If eternal inflation is correct, and if the properties that determine matter-antimatter symmetry vary between bubble universes, then we'd expect to find ourselves in a bubble where the asymmetry was just right for structure formation. Too much asymmetry, and the universe would be matter-dominated but potentially unstable in other ways. Too little, and everything annihilates. We observe what we observe because we couldn't exist to observe anything else. But there's a problem with relying too heavily on anthropic reasoning. It doesn't make new predictions. It doesn't tell us what to look for in experiments. If you can explain any observation by saying it's that way because otherwise we wouldn't be here, you've stopped doing physics in a certain sense. You've replaced testable mechanisms with selection effects. Most physicists prefer to look for actual mechanisms, processes that would make our universe the way it is, even if they acknowledge that anthropic considerations might play a role in some cases. The search is for theories that predict the matter-antimatter symmetry as a consequence of the laws and initial conditions, not as a lucky random outcome that we happen to observe because we couldn't observe anything else. There's also the question of what it would mean for other universes to exist. If they're completely causally disconnected from ours, if there's no way to ever observe or interact with them, are they real in any meaningful sense? Or are they just a mathematical possibility, a feature of our theories rather than of reality? These are deep questions at the boundary between physics and philosophy. But they matter because they affect how we think about explanation and understanding. Do we need a mechanism that makes our universe likely? Or can we accept that it might be unlikely but observable for selection reasons? My own sense, and this is just one perspective among many, is that we should keep searching for mechanisms. The matter-antimatter asymmetry seems too specific, too precisely balanced to be just a random outcome. 1 part in a billion. That's not a random number. It suggests a process, a mechanism, something that set that particular value. And we have candidates for such mechanisms: leptogenesis, electro-weak barriogenesis, various other scenarios all make specific predictions. They're testable, at least in principle. Some have already been partially tested and partially constrained. That's the kind of progress we can make with mechanistic explanations. The anthropic multiverse idea might turn out to be correct, but it should be a last resort, something we accept only if we exhaust all mechanistic explanations and find that the asymmetry truly seems arbitrary, truly random, with no underlying cause. We're not there yet. We still have plenty of avenues to explore. And there's something worth preserving in the search itself, in the refusal to simply shrug and say, quote, to quote. Because even if we did, even if our universe is one unlikely outcome among many, understanding why this particular outcome was possible, what processes could create it, what laws permit it, that's still worthwhile knowledge. That still tells us something deep about how reality works. So the multiverse question remains open. A possibility, yes. An explanation, maybe. But not yet the answer. Not while there are still mechanisms to discover, experiments to perform, measurements to make. The search continues, and it continues to yield insights, even if the final answer remains elusive. There's something aesthetically appealing about symmetry. When we see a perfectly symmetric pattern, a snowflake, a mandala, a crystal, we perceive beauty. Our minds find pleasure in balance, in harmony, in things that mirror themselves perfectly. And physics has long been guided by symmetry. The great discoveries of the 20th century, special relativity, general relativity, quantum mechanics. The Standard Model all rest on symmetry principles, the idea that the laws of physics should look the same from different perspectives, that nature shouldn't prefer one direction over another, one moment over another, one location over another. Symmetry has been such a powerful guide that physicists sometimes speak of it with almost religious reverence. There's an elegance to symmetric theories, a simplicity and inevitability. When you find the right symmetry, everything else follows. The equations almost write themselves. But the universe we're discovering is not perfectly symmetric. CP symmetry is violated. Matter outnumbers antimatter. The laws of physics have subtle preferences, small biases, tiny imperfections in the mirror. And this raises a philosophical question. Is symmetry breaking a flaw in nature, an imperfection that mars the perfect beauty of the underlying laws? Or is it a feature, something essential, something that makes complexity and structure and life possible? I think it's the latter. Perfect symmetry is beautiful, but it's also sterile. A perfectly symmetric universe, where matter and antimatter existed in exact balance, would annihilate completely. It would be uniform, simple, devoid of structure. Nothing interesting would happen. No stars, no planets, no chemistry, no evolution, no consciousness. The broken symmetries, the slight imperfections, are what allow for richness, for diversity, for the emergence of complex structures. They're what make the universe interesting rather than trivial. There's a parallel here with other broken symmetries in physics. The Higgs mechanism, which gives particles their mass, works through symmetry breaking. At high temperatures, all particles are massless, and the universe has a high degree of symmetry. But as the universe cools, the Higgs field settles into a non-zero value, breaking the symmetry and giving particles mass. This symmetry breaking is essential. Without it, there would be no atoms. Electrons and quarks would be massless, travelling at the speed of a light, unable to bind together into stable structures. The universe would be a soup of radiation. The flaw in the perfect symmetry is what makes matter possible. Similarly, the breaking of CP symmetry in the early universe, the small preference for matter over antimatter, is what makes our universe possible. The flaw is the feature. The imperfection is the prerequisite for existence. This has implications for how we think about the laws of nature. We're used to thinking of fundamental laws as symmetric, perfect, elegant, and in a sense they are. The underlying equations have beautiful symmetries, but the way those laws manifest in the actual universe involves symmetry breaking, phase transitions, emergent complexity. It's like how the laws governing water molecules are perfectly symmetric, but a snowflake forming from those molecules has a specific, unique pattern. The symmetry is still there in the laws, but the actual object that forms has less symmetry because of how the phase transition occurred, the specific path the system took. The universe we observe is the result of countless symmetry breakings, each one opening up new possibilities for structure and complexity. From the initial breaking that created space and time, through the phase transitions that gave particles mass and created the matter-antimatter asymmetry, to the formation of nuclei and atoms and molecules, each step involved broken symmetry. And here's what I find beautiful. The breaking isn't random. It's guided by the underlying symmetric laws. The laws permit the breaking, channel it, determine what kinds of asymmetries can emerge. Perfect symmetry plus contingent history equals the complex structured universe we observe. There's a kind of wisdom in accepting both aspects, the symmetric beauty of the fundamental laws and the asymmetric richness of the actual cosmos. We don't have to choose between them. The laws are symmetric. The universe is not. Both things are true, and both are necessary. This might be a good lesson for life in general, actually. Perfect balance is aesthetically pleasing, but practically impossible and perhaps not even desirable. Real richness, real depth comes from asymmetries, from differences, from the fact that things aren't perfectly uniform. A perfectly balanced life would be as sterile as a perfectly symmetric universe. What makes existence interesting, what allows for growth and change and surprise, is precisely the fact that things are out of balance. That there's a symmetry, that the universe took one path rather than another. We exist because the universe broke its own symmetry, because in the first microsecond something tipped the scales toward matter. That breaking, that tiny preference, that cosmic imperfection, is the reason for everything. And perhaps there's something profound in that, in the idea that existence itself requires a departure from perfect symmetry. That life is the child of broken balance. that we're here because the universe chose to be interesting rather than perfect. Antimatter has captured the popular imagination in a way that few other scientific concepts have. It appears in Star Trek as fuel for the Enterprise's warp drive. In Dan Brown's novel Angels and Demons, terrorists steal antimatter from CERN to use as a weapon. In particle physics jokes, it's the punchline about matter's evil twin. There's something irresistible about the idea of mirror matter, of substance that annihilates on contact with the ordinary world. Part of this appeal comes from the name itself. Antimatter sounds like science fiction. It has the same linguistic structure as anti-hero or antichrist. It's the opposite of something fundamental, the negation of matter itself. And the fact that it's real, that it actually exists in nature and can be created in laboratories, makes it even more compelling. But popular culture often gets antimatter wrong in interesting ways. In Star Trek, for example, the Enterprise carries antimatter in storage pods, using magnetic containment to keep it away from regular matter. When they need power, they let matter and antimatter mix in controlled amounts, releasing energy to power the ship. This isn't entirely wrong. Magnetic containment is indeed how we trap antimatter in real laboratories, but the scale is absurdly wrong. The Enterprise supposedly carries tons of antimatter. In reality, all the antimatter ever created by humanity would weigh far less than a grain of sand, and creating even that tiny amount required enormous energy inputs. The cost and difficulty of creating antimatter makes it impractical for any of the applications science fiction imagines. You can't mine it. There are no antimatter deposits in space. You can't generate energy by creating and annihilating it. You have to put in far more energy than you get back. And while the energy density of matter-antimatter annihilation is indeed enormous, the storage problem is essentially insurmountable for any quantity that would be useful as fuel. Dan Brown's Angels and Demons does slightly better with the physics, at least in acknowledging that antimatter is difficult to create and contains. The plot involves stealing a small amount of antimatter from CERN, which is plausible in principle, though the security around antimatter research is presumably better than the novel suggests, and the idea of antimatter as a weapon, while dramatic, overstates both its destructiveness and its practicality. A gram of antimatter annihilating with a gram of matter would release about 43 kilotons of energy, roughly 3 times the yield of the bomb dropped on Hiroshima. That's significant, but nuclear weapons are far easier to build and don't require particle accelerators. If you have the technology to create a gram of antimatter, you definitely have the technology to build nuclear weapons, and the latter would be vastly cheaper and more practical. But these exaggerations and misunderstandings aren't entirely bad. They've made people aware of antimatter, made it part of the cultural conversation. And they've inspired interest in real physics. Many physicists working in antimatter research today were first drawn to the field by science fiction, by the exciting possibility of studying something that seemed impossibly exotic. There's also antimatter in superhero comics, where characters gain powers from antimatter radiation, or travel to antimatter universes. These are pure fantasy, bearing no relationship to real physics, but they're fun. They play with the idea of opposites, of mirror worlds, of substances that are both incredibly powerful and incredibly dangerous, and in a way this cultural fascination reflects something real about antimatter's place in our understanding of the universe. It is exotic, it is rare, it does represent a kind of mirror image of the ordinary world. The fact that it exists at all is remarkable. The fact that we can create it and study it is even more remarkable. What popular culture gets right, even when it gets the details wrong, is the sense of wonder. The idea that reality includes not just the matter we see around us, but also this shadow substance, this antimatter that can briefly flicker into existence before vanishing. That the laws of physics are more symmetric, more inclusive than everyday experience suggests. And there's value in that wonder, in the way scientific discoveries can capture the imagination. Because wonder is what drives curiosity. Curiosity is what drives research, and research over time leads to understanding. The scientists at CERN trapping individual antihydrogen atoms aren't thinking about warp drives or antimatter bombs. They're thinking about fundamental symmetries, about the matter-antimatter asymmetry, about the deep questions of why the universe is the way it is. But the fact that antimatter has cultural resonance, that people care about it even outside the scientific community, makes it easier to justify the enormous investments required for these experiments. Public fascination might be based partly on misunderstandings, but it's also based on genuine wonder at the strangeness and beauty of reality. And that's something worth preserving, worth encouraging, because the real story of antimatter, the actual physics, the experiments, the cosmic mystery, is every bit as fascinating as the science fiction and far more profound. After all the experiments, all the measurements, all the theoretical work spanning decades, what don't we know about antimatter? Quite a lot, it turns out. The matter-antimatter asymmetry remains one of the great unsolved problems in physics, right up there with dark matter and dark energy, and the nature of quantum gravity. We don't know which process created the asymmetry. Was it leptogenesis through heavy neutrino decay? Was it electroweak baryogenesis during the Higgs phase transition? Was it something else entirely, involving particles and forces we haven't discovered yet? We have candidates, but no definitive answer. We don't know the precise value of the CP violating phase in the neutrino sector, though experiments are gradually measuring it. We don't know if neutrinos are Majorana particles, their own antiparticles, or if they're Dirac particles, distinct from their antimatter twins. This is a fundamental question about the nature of neutrinos, and we're still working on answering it. We don't know if there are additional sources of CP violation beyond what's in the standard model. The CP violation we've measured in quark interactions is too small to explain baryogenesis. There must be more, but where is it? What particles or forces carry this additional CP violation? We don't know if antimatter gravitates exactly like matter. The alpha-G experiment showed it falls down, not up, which rules out some exotic theories. But the precision of that first measurement leaves room for subtle differences. Does antimatter fall at exactly the same rate as matter, to 1 part in a billion? Or is there a tiny difference that could point to new physics? We don't know if there are any large-scale regions of antimatter in the universe. Our searches for gamma-ray signatures of matter-antimatter boundaries have come up empty. But we can only observe so far. Could there be antimatter galaxies beyond our observational horizon? Probably not, but we can't rule it out completely. We don't know the exact energy scale at which baryogenesis occurred. Was it during the electroweak phase transition, at about 1/1000th of a second? Or was it much earlier, during a phase transition involving grand unified theories, or some aspect of inflation? The timing affects what kinds of processes could have been involved. We don't know if the laws of physics have changed since the early universe. The parameters we measure today, particle masses, coupling strengths, symmetry-breaking scales, might have been different when the universe was younger and hotter. If they've evolved, it could affect our understanding of baryogenesis. We don't know if CPT symmetry is truly exact. It's believed to be a fundamental requirement of quantum field theory, but we've only tested it to limited precision. Could there be tiny violations of CPT symmetry that we haven't detected yet? If so, they would point to physics beyond quantum field theory, something even more fundamental. We don't even know for certain that the matter-antimatter asymmetry is uniform throughout the observable universe. We assume it is based on our observations, but what if there are local variations? What if some regions have slightly more matter than others? Could this affect structure formation or galaxy evolution? These are not idle questions. Each one represents an active area of research, with experiments designed to address it, theorists working on models, observers searching for relevant data. The unknowns drive the field forward, defining the frontier of our understanding. And in some ways, the unknowns are as valuable as the knowns, They tell us where to look next, what questions to ask, what experiments to build. They remind us that our understanding is incomplete, that there's more to discover. There's a humility in acknowledging what we don't know, and a kind of excitement too. Because unknowns represent opportunity. They represent the possibility that tomorrow's experiment might reveal something unexpected, that next year's observation might solve a decades-old puzzle, that the next generation of physicists might see patterns we're missing. The history of antimatter research has been full of surprises. Dirac predicted it from pure mathematics. Anderson discovered it in cosmic rays. Scientists learned to create it in accelerators, trap it in magnetic bottles, measure its properties with extraordinary precision. Each step revealed something new, something that wasn't obvious from the beginning, and the biggest mysteries remain unsolved. Why does the universe exist? Why matter instead of nothing? The answer, when we find it, might be simple and elegant, or it might be complex and surprising, or it might lead to even deeper questions that we can't yet imagine. But that's the nature of fundamental physics. You answer one question and 3 more appear, you solve one mystery and discover 10 more behind it. The horizon of knowledge recedes as you approach it. And that's okay. That's more than okay. That's what keeps the enterprise alive, what makes it worth pursuing. Because the questions matter. Understanding matters. And the search for understanding, even when it doesn't lead to immediate answers, teaches us things about reality, about ourselves, about what's possible. The study of antimatter, the rarest substance in the universe, has revealed fundamental truths about existence itself, and there are more truths waiting to be discovered. Let's think about what it means that the universe made a choice, even if it wasn't a conscious choice, even if it was just physics playing out according to laws we don't fully understand. In the first microsecond after the Big Bang, when matter and antimatter were being created in equal pairs, annihilating, creating, annihilating, something broke the perfect balance. 1 extra matter particle for every billion pairs. That's all it took. That's the margin by which we exist rather than not existing. There's something vertiginous about contemplating this. If you could rewind the universe to that first microsecond and let it play forward again, would the same asymmetry emerge? Or was there an element of chance, of quantum randomness that could have gone differently? We don't know. If leptogenesis is correct, if the asymmetry came from the decay of heavy Majorana neutrinos, then there was probably randomness involved. These decays are quantum mechanical processes, probabilistic at their core. Each individual neutrino had a certain probability of decaying into matter leptons versus antimatter leptons. And the overall asymmetry emerged statistically from trillions upon trillions of these random decays. It's like flipping a coin that's ever so slightly biased. Not 50-50, but 50.00001% to 49.999999%. Flip it a few times and you might not notice the bias. Flip it a trillion times and the bias becomes obvious. The side with the tiny advantage accumulates more results. In the early universe, that accumulation happened in a fraction of a second. The biased quantum coin was flipped countless times in the hot, dense, rapidly expanding cosmic fireball. And when the flipping stopped, when the temperature dropped below the threshold for creating new particles, matter had a slight edge. But it could have gone the other way. It's possible that some regions of the multiverse, if the multiverse exists, ended up antimatter dominated. Or it's possible that the bias is deterministic, that the laws of physics guarantee matter wins. We don't know yet. What we do know is that this cosmic choice, this symmetry breaking in the first instant, determined everything that followed. It set the initial conditions for 14 billion years of cosmic evolution. After the asymmetry was established, after all the antimatter found matter partners and annihilated, what was left was a universe made of matter, filled with photons from the annihilation, expanding and cooling. Gradually, over hundreds of thousands of years, that matter clumped together under gravity's pull. The tiny density fluctuations from the inflationary era grew into larger and larger structures, Eventually the first stars formed, igniting nuclear fusion in their cores. They lived, evolved, exploded as supernovae, scattering heavy elements into space. New generations of stars formed from the enriched material, some with planets. On at least one of those planets, around an ordinary star in an ordinary galaxy, chemistry became biology. Biology became consciousness. And consciousness began asking questions about its own origins. All of this traces back to that first microsecond, to the matter-antimatter asymmetry, to the cosmic choice that made existence possible. If the asymmetry hadn't happened, none of this would exist. No stars, because there would be no hydrogen to fuel them. No planets, because there would be no elements to build them. No chemistry, no life, no observers, no questions. Just an expanding sea of photons, growing forever colder and more dilute, carrying the energy of what might have been but never was. There's a kind of fragility in realizing this. We exist on such a knife's edge, dependent on an asymmetry that's only one part in a billion. It's not that the universe is fine-tuned for life. That's a different discussion. It's that the universe barely avoided being completely empty. The margin was razor thin. And yet here we are, not just existing, but aware of our existence, capable of tracing it back to its origins, of understanding the physical processes that made us possible. We're matter contemplating the fact that it defeated antimatter. We're the descendants of that cosmic victory, asking why it happened, how it happened, what it means. Perhaps there is no meaning beyond the physics. Perhaps the asymmetry is just a brute fact, a contingent historical event that happened for mechanistic reasons we'll eventually understand. Purpose and significance are things we create, not things we discover in the structure of fundamental particles. But still there's something worth pausing over in the realization that you exist because of quantum processes in the first microsecond of cosmic history. That every atom in your body is matter, because the universe's quantum coin came up matter just slightly more often than antimatter. That you're made of the residue, the survivor, the tiny surplus that remained after the cosmic fire. You're rare. Not individually. There are billions of people, countless living things. But collectively, as matter, as structure, as complexity, we're the rarest thing in the universe. We're the one part in a billion that survived. We're what the universe became after choosing to exist rather than not exist. And that's worth contemplating, worth feeling grateful for, even if we don't fully understand why it happened. There's an aesthetic dimension to the matter-antimatter asymmetry that we haven't fully explored yet. The idea that the universe is more beautiful, more interesting, because it's asymmetric rather than perfectly balanced. Think about art for a moment. Perfect symmetry can be striking. A mandala, a classical building with its mirror image wings. But often the most compelling art has asymmetry, tension, imbalance. A photograph with the subject slightly off-centre following the rule of thirds. A musical phrase that resolves but not where you expected. A story that veers away from the expected symmetrical arc. Asymmetry creates interest because it creates directionality, narrative, a sense that something is happening rather than just existing in static perfection. The universe's matter-antimatter asymmetry does the same thing. It created a direction, a narrative, a history. In a perfectly symmetric universe, with equal matter and antimatter, nothing would happen. Or rather, one thing would happen. Complete annihilation. And then nothing else, ever. The story would be one sentence long. Beginning, annihilation, end. No second chapter. The asymmetry allowed for sequels, allowed for a story that continues. After the annihilation came nucleosynthesis, the formation of light elements. After nuclear synthesis came the cosmic dark ages, when the universe was filled with neutral hydrogen but no stars yet. After the dark ages came the first stars, reionizing the universe with their light. After the first stars came galaxies, clusters, the cosmic web. And the story is still unfolding, stars are still forming, planets are still evolving, life is still adapting, changing, creating new forms and possibilities. The narrative continues because the asymmetry gave it fuel, matter to work with, structure to build on, complexity to emerge from. In mathematics and physics, there's something called spontaneous symmetry breaking. This is when a system that has a certain symmetry in its laws nevertheless settles into an asymmetric state. The classic example is a pencil balanced on its point. The laws governing the pencil treat all directions around it equally. Perfect rotational symmetry. But the balanced state is unstable. The pencil will fall, and when it does, it will choose a direction. That choice breaks the rotational symmetry. The early universe was similar in a way. The laws of physics had a high degree of symmetry, matter and antimatter treated equally, at least approximately. But the state was unstable, or rather, the universe was evolving too rapidly for perfect balance to maintain itself. Quantum fluctuations, phase transitions, and the CP violating processes we've discussed allowed the universe to tip toward matter. The symmetry spontaneously broke, but unlike the pencil, which just falls and stops, the universe's symmetry breaking had lasting consequences. It wasn't just that the universe chose matter over antimatter in one moment, and then that was that. The choice set in motion everything else. It was a creative act in a sense, not conscious, not deliberate, but creative in its outcomes. There's a parallel here with biological evolution. The genetic code could have been different. The chemistry of life could have taken other forms. The fact that DNA uses the specific bases it does, that proteins fold the ways they do, is partly historical accident. The first self-replicating molecules happened to use certain chemical pathways, and all subsequent life inherited those choices. Similarly, the universe happened to break toward matter, and all subsequent structure inherited that choice. We're descendants not just of the first living cells, but of the first asymmetric moment, the first breaking of cosmic symmetry. And there's beauty in this inheritance, in the way ancient choices reverberate through time, constraining and enabling everything that follows. The specific amino acids that build your proteins trace back to chemistry that emerged in ancient seas. The specific atoms that make up your body trace back to stars that exploded billions of years ago. And the fact that you're made of matter rather than antimatter traces back to the first microsecond of cosmic history. You carry within you the history of the universe, not metaphorically but literally. The hydrogen in your water was forged in the Big Bang. The carbon in your cells was cooked in stellar cores. The iron in your blood was synthesized in supernova explosions, and the matter itself, the stuff you're made of, is the survivor of the cosmic lottery, the residue after the great annihilation. This isn't mysticism, it's physics, chemistry, cosmology, but it's also profound. It connects you to the larger scales of space and time. You're not separate from the cosmos, you're a part of it, a continuation of it, a way the universe has organised itself to become aware of itself, and the asymmetry made it possible. The broken symmetry, the imperfect balance, the cosmic choice that favoured matter. If the universe had been perfectly symmetric, you wouldn't exist to contemplate its symmetry. If the laws had been perfectly balanced, there would be nothing to experience that balance, so perhaps we should be grateful for the imperfection. For the fact that the universe is interesting rather than ideal, complex rather than simple, asymmetric rather than perfectly balanced. Because that asymmetry, that departure from perfect elegance, is what allowed for everything we know and experience and are. Let's bring this back to something personal for a moment, to where you are right now, reading or listening to these words. You're here because antimatter lost the cosmic lottery. You're made of matter because in the early universe, matter slightly outnumbered antimatter. Every atom in your body is a descendant of that tiny surplus, that one part in a billion asymmetry. But you're also here because humans got curious, because we wondered about the nature of reality, because scientists asked questions and built experiments and spent decades creating antimatter one atom at a time just to understand it better. The antimatter in CERN's traps exists because we made it exist. We took energy from our electrical grids, energy ultimately from the sun, from nuclear fusion in our local star, and we transformed it into particles of antimatter. We recapitulated in a tiny controlled way the physics of the early universe. We created matter and antimatter from pure energy, then trapped the antimatter and studied it. This is a remarkable capability when you think about it. We're matter that's learned to create antimatter. We're the universe's way of studying its own history, its own fundamental structure. Consciousness emerged from matter, and consciousness invented science. And science discovered antimatter, and now we're using antimatter to understand why matter exists in the first place. There's a lovely circularity to this. The matter-antimatter asymmetry allowed matter to survive and form structures. Those structures became complex enough to evolve life. Life became complex enough to develop intelligence. Intelligence became sophisticated enough to invent physics. And physics discovered that intelligence exists only because of an ancient asymmetry that we still don't fully understand. We're part of the story we're trying to tell. We're not objective observers standing outside the universe, looking in. We're patterns within it, temporary structures made of matter, asking questions about our own existence. And those questions lead to experiments, to particle accelerators and magnetic traps and precision spectroscopy, to searches for CP violation and tests of gravity's effect on antimatter, to theoretical work on baryogenesis and leptogenesis and phase transitions in the early universe. All of this is humans trying to understand where we came from, why we're here, what the universe is made of. It's the same impulse that drove our ancestors to look at the stars and wonder, to develop calendars and cosmologies and creation myths. But now we have mathematics, we have experimental methods, we have technologies that let us probe reality at the smallest scales and test our ideas rigorously. And what we've learned is humbling. We exist because of an asymmetry so slight it almost didn't happen. We're the accidental survivors of a cosmic event we can barely understand. Everything we've built, everything we've achieved, every thought we've had depends on that ancient mysterious imbalance between matter and antimatter. But here's what's equally remarkable. Despite our cosmic insignificance, despite existing only because of a 1 part in a billion fluke, we've been able to figure this out. We've traced our origins back to the first microsecond. We've discovered antimatter and learned to create it. We've measured the baryon to photon ratio and calculated how much matter and antimatter must have annihilated in the beginning. This is consciousness doing what consciousness does best, making sense of its surroundings, building models, testing them, refining them, approaching truth asymptotically. We might not have all the answers yet. We might never have all the answers. But we're asking the right questions and we're making progress. You're part of that progress, in a way. By learning about antimatter, by thinking about the matter-antimatter asymmetry, by engaging with these ideas, you're participating in humanity's collective effort to understand the cosmos. You're not just a passive product of the Big Bang, you're an active investigator of it, and there's something beautiful in that active role. We're not just matter. We're matter that knows it's matter. We're the universe's way of knowing itself, of understanding its own history and structure and laws. Every time someone learns about antimatter, every time someone grasps why the asymmetry matters, the universe becomes a little more self-aware. This might sound grandiose, but it's just description. Consciousness is a physical process. Neurons firing, patterns emerging in the complexity of brains. And when those patterns represent knowledge about physics, about cosmic history, about the nature of matter and antimatter, that's literally the universe containing information about itself. You are a part of that. Your brain, made of matter, processing information about why matter exists, your thoughts tracing back through the chain of causation, from your immediate experience to the structure of atoms, to the physics of the early universe, to the fundamental laws that make everything possible. This is what it means to be conscious in a cosmos governed by physical law. You're embedded in the system you're trying to understand. You're made of the stuff you're studying. Your existence proves the phenomenon you're investigating. The asymmetry that made you possible is the asymmetry you're contemplating. And perhaps that's the most profound thing about the matter-antimatter story. It's not just ancient history. It's not just abstract physics. It's personal. It's about you, your origins, your existence. You're here reading these words because 13 billion years ago, quantum processes in a hot dense fireball created slightly more matter than antimatter. You're a consequence of that asymmetry, a descendant of it, a continuation of it, and now you know it. The future of antimatter research stretches ahead with possibilities both practical and profound, and while we don't know exactly where it will lead, we can see some of the questions scientists are actively pursuing, experiments they're building, measurements they're planning. There are next-generation antimatter experiments under development at CERN and other facilities that will trap antihydrogen with even greater precision, hold it for even longer periods, measure its properties to even finer detail. The goal is to compare matter and antimatter at the level of parts per trillion or better, searching for any deviation, any hint that antimatter is not a perfect mirror of matter. If such a deviation were found, it would be revolutionary. It would point to new physics beyond the standard model. New forces or particles that affect matter and antimatter differently. It could help explain the cosmic asymmetry, or reveal entirely new aspects of how the universe works. There are also plans to test antimatter in ways never attempted before. Experiments to measure how antimatter falls in Earth's gravity, with much higher precision than the initial alpha-G results. Tests of whether antimatter has the same inertial mass as matter when accelerated. Searches for extremely rare processes that might violate CPT symmetry, the deepest symmetry we know. Each of these measurements pushes at the boundaries of what's technically possible. Trapping antimatter long enough to measure how it falls requires exquisite control. Measuring its properties with parts per trillion precision requires lasers stable to 1 part in a quadrillion. Magnetic fields controlled to extraordinary precision. Vacuum conditions better than outer space. But physicists are getting better at this. The techniques for handling antimatter have improved dramatically over the past few decades. What was impossible in the 1990s became difficult in the 2000s and became routine in the 2020s, and this progress continues. There are also theoretical developments to watch, new models of baryogenesis that make testable predictions, refined calculations of CP violation in various processes, better understanding of phase transitions in the early universe. Each theoretical advance suggests new observations to make, new experiments to perform, and there are connections to other areas of physics that might provide clues. Dark matter research, for instance, could intersect with antimatter physics if dark matter particles turn out to be their own antiparticles, Majorana particles like neutrinos might be, or if dark matter annihilates with itself, producing antimatter signatures that might be detectable. The searches for neutrinoless double beta decay continue, getting more sensitive each year. If this process is discovered, it would prove neutrinos are Majorana particles, and strengthen the case for leptogenesis as the explanation for the matter-antimatter asymmetry. If it's not found after exhaustive searching, it would constrain the models and point toward alternative explanations. There are also astrophysical observations that could inform our understanding. Better measurements of the cosmic microwave background might reveal signatures of phase transitions in the early universe. Gravitational wave observations might eventually detect the background of waves from the electroweak phase transition or earlier events. Measurements of primordial element abundances might constrain when and how baryogenesis occurred. All of these approaches are complementary. Laboratory experiments, theoretical calculations, and astronomical observations all contribute pieces to the puzzle. And gradually, over years and decades, the picture becomes clearer. But there's also the possibility of surprises. Physics has a history of unexpected discoveries that change everything. The existence of antimatter itself was such a surprise, predicted by mathematics but not expected. The discovery of CP violation was a surprise. The realization that neutrinos have mass was a surprise. Dark matter and dark energy were surprises. The matter-antimatter asymmetry might be explained by physics we already know, just combined in ways we haven't fully worked out yet. Or it might require completely new physics, particles and forces we haven't imagined. We won't know until we know, and that's okay. The uncertainty, the unknowns, the questions still hanging in the air, these aren't failures of science. They're the frontier. They're what makes the field alive, what drives research forward, what makes the next experiment worth doing. Some of the people reading or listening to this might end up working on these problems. Explains baryogenesis. The questions are explains baryogenesis. The questions are open. The field needs people asking them, people willing to spend years on problems that might not have answers. Because even if we never fully solve the matter-antimatter mystery, the attempt teaches us things. About particle physics, about the early universe, about experimental technique, about how to ask precise questions and build instruments capable of answering them. The search for understanding is valuable even when understanding remains elusive. And there's also something worth preserving in the not knowing. A mystery. A genuine puzzle about reality that we haven't solved yet. These are rare in science. Most questions have tentative answers, working models, good enough explanations. But the matter-antimatter asymmetry remains deeply mysterious. We know it happened. We don't know how. And that gap between knowing and understanding is where the most interesting science lives. As we approach the end of our journey through Antimatter's story, I find myself returning to something simple, something emotional rather than scientific. Gratitude. Gratitude for the asymmetry that made everything possible. This might seem like an odd thing to feel grateful for. The matter-antimatter imbalance wasn't created for us. It wasn't designed to allow our existence. It's a physical process, a consequence of laws and initial conditions and quantum randomness in the early universe. There's no intent behind it, no purpose, no meaning except the meaning we assign. But still, there's something worth acknowledging in the fact that we're here because of it. That existence itself, the entire rich complexity of the cosmos we inhabit, traces back to a tiny imbalance in the first microsecond of time. Think about what that asymmetry gave us. It gave us stars, vast nuclear furnaces that shine for billions of years, creating and distributing the heavy elements necessary for planets and life. It gave us galaxies, those island universes containing hundreds of billions of stars organised into beautiful spirals and ellipses by the interplay of gravity and motion. It gave us planets, worlds of rock and metal and ice, some with atmospheres, some with oceans, some with the delicate conditions necessary for chemistry to become biology. It gave us the long, slow evolution of complexity, from simple molecules to self-replicating systems, to cells, to multicellular organisms, to intelligence. And it gave us this moment, right now, you and me, consciousness contemplating its own origins. The asymmetry made minds possible, and minds made science possible, and science discovered the asymmetry. There's a completion to this circle, a kind of cosmic self-reflection. You might ask, grateful to what? To whom? The asymmetry wasn't a gift, it's just physics, and that's true. But gratitude doesn't require a giver. It's an attitude, a way of relating to existence, a choice to acknowledge and appreciate rather than simply take for granted. We exist against absurdly long odds. Not just the odds that life would emerge on this particular planet, or that your particular set of genes would come together to make you. But the more fundamental odds that matter would exist at all, that the universe wouldn't be empty, that the cosmic coin flip would land on existence rather than oblivion, 1 part in a billion. That's how close we came to not being. If the asymmetry had been slightly smaller, maybe too much matter would have annihilated, leaving too little to form stars. If it had been slightly larger, maybe the universe would have evolved differently, in ways incompatible with complexity and life. The margin was narrow. The asymmetry was precisely what it needed to be, not because the universe was trying to create us, but because we're the kind of thing that emerges when the asymmetry has the value it has. We're a consequence, not a goal. But what a remarkable consequence. And here's what moves me most about the antimatter story. It's a reminder that existence is contingent, precious, unlikely. We're not guaranteed. We're not necessary. We're possible because of specific physics. Before I say goodnight, I need you to know something. When this video was posted, most people scrolled right past it. They saw the length, they saw the topic, and they kept scrolling. But you didn't. You stayed for 2.5 hours, you chose depth over speed, and wonder over noise, and I think that says something beautiful about the kind of person you are. If this channel has given you something tonight, a little more peace, a little more wonder, a little more understanding of the world you live in, then a like and subscribe is the kindest thing you can leave behind before you sleep. Not just for this channel, but for the next person out there tonight who needs exactly what you just found here. Now, rest. You have earned it. We're possible because of specific physical laws and specific historical events and specific initial conditions. Change any of these and we might not be here. This contingency, this fragility, makes existence more valuable, not less. It means we're a kind of cosmic accident, yes, but a beautiful accident. An accident that led to stars and planets and minds and love and art and science and all the rich texture of conscious experience. The matter-antimatter asymmetry is one of the foundational accidents that made everything else possible. And while we might eventually understand the mechanism, while we might figure out exactly which particles and processes created the imbalance, that understanding won't make it less remarkable. It will just make it more specific, more detailed, more precise. We'll still be here because of an asymmetry. We'll still be the descendants of that cosmic lottery. We'll still be matter contemplating the fact that antimatter lost. And perhaps that's enough. Perhaps we don't need cosmic purpose or design or intention. Perhaps the fact that we're here, that we can ask these questions, that we can trace our origins back to the beginning and marvel at the chain of causation. Perhaps that's sufficient basis for gratitude. I'm grateful for the asymmetry because it led to you, to your consciousness, your experience, your ability to wonder and question and understand. You're a way the universe has organized itself to become aware of itself, and the asymmetry is part of your origin story. As fundamental as any creation myth but verified by evidence and calculation and experiment. So as our exploration of antimatter draws toward its close, let's rest in this gratitude for a moment. Gratitude for the cosmic accident that made us possible. Gratitude for the broken symmetry that allowed structure to emerge. Gratitude for the 1 part in a billion surplus that survived the annihilation and became everything we know. We're here. Against the odds. Because of an asymmetry we're still working to understand, and that's remarkable. That's worth appreciating. That's worth the slow drift of thought we've taken together through these hours, following the thread from the rarest substance in the universe back to the origin of everything, and discovering ourselves there in that first microsecond already implicit in the cosmic choice that favoured matter over antimatter. Existence over oblivion. Thank you for staying with me on this long journey through the story of antimatter. We've travelled together for nearly 2.5 hours now, from the theoretical predictions of Paul Dirac to the underground laboratories at CERN, from the first microsecond of cosmic history to the present moment, right here, right now. We began with a simple question. Why does the universe exist? Why is there something rather than nothing? And the answer, as honestly as I can give it, is that we don't fully know. We know an asymmetry must have occurred, a 1 part in a billion preference for matter over antimatter in the early universe. We know this asymmetry allowed matter to survive the primordial annihilation. We know that survival made everything else possible. But the mechanism remains mysterious. Whether it was leptogenesis through heavy neutrino decay or electro-weak baryogenesis during a phase transition, or something else entirely, we're still working it out. The experiments continue, the measurements get more precise, the theories get refined. And gradually, we're approaching an answer. Perhaps the answer is that the universe simply broke toward matter for reasons that are fundamentally random, quantum mechanical, unpredictable. Perhaps there's a deeper deterministic mechanism we haven't discovered yet. Perhaps there are countless other universes where the symmetry broke differently, or didn't break at all, and we're here simply because we couldn't be anywhere else. What we've learned, though, is that existence itself is remarkable. That you're here because of physics operating at the smallest scales in the earliest moments of time. That every atom in your body is a descendant of the cosmic lottery, the tiny surplus that remained after the Great Annihilation. You're made of stardust, yes, that's the common phrase. But more fundamentally, you're made of the matter that defeated antimatter. You're the survivor. If you enjoyed this slow drift through one of the universe's deepest mysteries, a like and subscribe would be wonderful. It helps others find these calm explorations of the cosmos. And if you have thoughts about antimatter, about existence, about the questions we've explored, I'd love to hear them in the comments. This community of people seeking peaceful ways to learn and drift into sleep is something special. Thank you for being part of it, wherever you are in the world right now. Wherever you're listening from, I hope you're comfortable. I hope your breathing has slowed, deepened, become more regular. I hope your thoughts have quieted, the urgencies of the day have faded, and your body feels heavy and warm and ready for rest. Look up at the stars if you can, or imagine them if you can't see them from where you are. All those points of light, each one a sun, each one fusing hydrogen into helium in its core, each one made of matter because 13 billion years ago, matter slightly outnumbered antimatter. The universe chose to exist in a sense. It broke toward complexity rather than simplicity, toward structure rather than uniformity, toward us rather than oblivion. You're part of that choice, not because you were intended, not because you were planned, but because you're what matter does when it has 14 billion years to organise itself. Your complexity made conscious. You're the universe looking at itself and asking questions about its own existence. And perhaps that's what antimatter teaches us most clearly, that existence is precious because it's contingent. We're here not because we had to be, but because the conditions were right. The asymmetry was just large enough, the laws were just so. We're a cosmic accident that became capable of understanding its own accidental nature. And there's a beauty in that, a profound beauty, a reason for gratitude even in the absence of a giver. So sleep well tonight, knowing you're made of matter that survived the cosmic fire. Dream, if you dream, of particles and antiparticles dancing in the early universe, of the tiny imbalance that made everything possible, of magnetic traps holding single atoms of the rarest substance in existence. Dream of scientists working underground, chasing mysteries, asking questions about why we're here. And know that these questions, these searches, these careful experiments and precise measurements, they're all humans doing what humans do best. Wondering, questioning, refusing to accept existence as simply given, wanting to understand, that impulse, that curiosity, that drive to know. It's as much a part of what makes us human as anything else. The antimatter story isn't finished. We're still writing it, still discovering, still refining our understanding. The next chapter might be written by someone listening to this right now, someone who decides to study physics, to work on these problems, to push the boundaries of what we know just a little bit further. But for tonight, let it rest. Let the questions settle. Let the mysteries be mysterious. There's a peace in not knowing, in accepting that some things are still unknown. that reality contains depths we haven't fully plumbed. Tomorrow the search continues. Tonight, rest. Thank you for joining me on this exploration. Thank you for your time, your attention, your curiosity. Thank you for being here, for existing, for being part of the universe's ongoing investigation of itself. Good night. Sleep well. And when you wake, may you carry with you a little of the wonder we've touched tonight. The wonder that you exist at all, that we exist, that the universe chose matter over antimatter, and in doing so made possible everything we know and love and are. Dream peacefully, rest deeply. The antimatter is in its magnetic traps at CERN, held safely away from the world, and you are here, made of matter, safe in your bed, and the universe continues its expansion, its cooling, its long journey from that first fierce moment toward whatever comes next. Good night.